Ready to learn mathematics behind machine learning, generative AI, or cutting-edge tech? Then you are in the right place. Today we are going to learn linear algebra like never before. In this crash course, in 6 hours, we are going to learn the basics and the fundamental concepts in linear algebra, a fundamental part in mathematics when it comes to many applied sciences. Our crash course in Fundamentals to Linear Algebra will be a great starting point for anyone who wants to refresh their linear algebra knowledge or who wants to start with the fundamentals of mathematics for AI, data science, machine learning, or generative AI. So if you are looking for that one course to refresh your memory in those fundamental concepts and be able to create your own algorithms and create your own AI-driven products, then you are in the right place. And if you're really serious about your education and career and backup with your mathematical foundations, then you can also check our 25+ hour comprehensive Fundamentals to Linear Algebra course, which is also part of our mathematics bootcamp. So check out lunartech.ai and you can get this comprehensive 25+ hour course along with the certification in linear algebra. So here's what we are going to cover as part of our Fundamentals to Linear Algebra crash course. So we are going to start with the introduction to linear algebra. We are going to talk about the prerequisites, what is exactly that you need in order to get into linear algebra, whether as a student, as part of your undergrad or graduate studies, or as a working professional who wants to learn the mathematics in a good way in order to become a well-rounded professional, whether it is for your future in quantum physics, in the future of data science, machine learning, or artificial intelligence. So we are going to learn the basics of the vectors. This is the first section that we are going to cover. Here we are going to learn the vectors, their basic definitions, the theory, but also the examples. So in this course, we are not just going to scratch the surface. We are going to dive deep. And the idea is that even for those basic concepts, we are going to learn not just the theory, the basic definitions, but we are also going to implement them in different examples. We are going to manually solve different examples by hand in order to truly master and practice this topic. And beside this, we are also going to talk about the applications of them across different domains, including in data science and AI. The idea is that those basic concepts are your starting point in the field of linear algebra. Because to truly understand this topic and to truly understand this entire linear algebra field, at least the course, the academic level course that you are used to seeing as part of the different advanced mathematical studies, you will need to dedicate more than just 6 hours. So if you are serious about your education and career and you want to learn mathematics from ground up, then check also our 25+ hour complete Fundamentals to Linear Algebra course to truly master the entire linear algebra in a very economic and efficient way, which contains an entire semester equivalent material, theory, practice, and the applications. So here's what we are going to cover as part of our crash course. So we will start with the introduction to linear algebra. We will talk about this concept of linear algebra. We will see what are the prerequisites in order to even understand and start with this course. We are going to refresh our memory with the different fundamental concepts. Here, in this Introduction to Linear Algebra section, we are going to quickly cover the prerequisites that you must know in order to get started with linear algebra. Here, I'm also going to refresh our memory on the fundamental concepts like real numbers and vector spaces, the norm of a vector, the Cartesian coordinate system, and also the angles, trigonometry, the norm versus Euclidean distance, Pythagorean theorem, etc. So after this, we are going to finally kickstart the linear algebra concepts. So first up, we are going to talk about the basic vector spaces. Here we are going to cover the definition of the vectors, what are vectors, the basic representation of it, but also the indexing of it, and how we can apply different simple operations like vector addition, vector subtraction, and also scalar multiplication. After this, in the next section, we are going to talk about the matrices and the basic operations. We are going to truly understand the matrices, the basic definition of them. We are going to see many examples of matrices and also in practice what are the basic operations that we can apply to matrices, including the additions, the scalar multiplication, and subtractions. After this, we are going to look into the dot product and the vector length. In this section, we are going to talk about the idea of dot product, what is this difference between dot product and inner product, understand the fundamentals of dot product and how they are calculated. We are going to complete many examples as this is a very important topic, especially for data science, machine learning, and AI. And once we are done with this, we will also look into this concept of the length of a vector and how this is related to, for instance, cosine rule and these different inequalities when it comes to the vector spaces. After this, we are going to look into the basic linear systems, how we can solve a linear system by using the infamous Gaussian elimination. Here we are going to talk about this basic concept of solving linear equations with many unknowns using the concept of matrices. We are going to see detailed examples where manually, step by step, by hand, we are going to derive the entire process using Gaussian elimination, how we can solve the system of linear equations, first getting the augmented matrix, and then this concept of reduced row echelon form, so REF and then RREF, so row echelon form and reduced row echelon form. And we are going to look into two different scenarios to ensure that we understand this intuition behind solving these linear systems in various type of cases. Then we are going to finish off the crash course with the preview of the advanced concepts. We are going to see the special matrices, we are going to see symmetric matrices, diagonal matrices, and then the idea of null matrices, Schwarz matrices, how they are used and why they are used commonly in programming. And then we are going to see a glimpse of how linear algebra can be applied across real-world scenarios. So, in this crash course, we are not just going to cover the quick definitions, but we are going to dive deep. We are going to truly try to understand those concepts, those geometric intuition and interpretation behind those concepts, and how they are related towards many applied sciences. So, to truly understand how each of those concepts are actually implemented in the real world, like in the fields of data science, statistics, and AI. This course is perfectly tailored for working professionals who need to sharpen their math skills, who want to quickly and efficiently refresh their memory, whether it's before their interviews, or who want to learn machine learning and statistics and AI, but they don't have the mathematical background. And instead of just going and studying at university like I did, and spending many years to do an undergraduate studies in mathematics or statistics, instead, you can just follow this course to quickly refresh your memory. But if you truly want to understand all the concepts, which is equivalent to 1 semester of linear algebra course, then definitely check out our 25+ hour Fundamentals to Linear Algebra course as part of our Mathematics Bootcamp at LoyalTech.ai. Because you can't master linear algebra in just 6 hours. So if you are a student, this course will also be a good way for you to refresh your memory if you are at the end of your deadline and you are about to complete your linear algebra exam. And if you want to learn everything from scratch and you have the time, then you can also check out 25+ hour course to learn the linear algebra fully and to ace your exams. This crash course is just the beginning for you. In this way, you are laying a solid foundation to become a well-rounded professional and to truly understand this topic of linear algebra. So if you're ready, I'm really excited, so let's get started. Welcome to the Mathematics for Data Science and AI Roadmap in 2024. Today we are going to discuss the roadmap behind a topic that powers many algorithms, the linear algebra. We are going to talk about all the concepts and the topics that you must know in order to master the linear algebra, which is the backbone of data science, machine learning, generative AI, and many other topics and cutting-edge tech. Whether you are aspiring to become a data scientist or AI professional, this is your starting point to learn the mathematics of data, the fundamentals of linear algebra. If you want to become a good professional, a well-rounded data scientist, and master the art of machine learning, generative AI, and many other cutting-edge tech domains, then your starting point should be to learn the mathematics, to truly understand these different mathematical concepts that power the algorithms behind the scenes, including many infamous algorithms like the GPT series or the BERT or transformers. Linear algebra is the mathematics of data. It's about the vectors, matrices, projections, and how to solve a system of linear equations and how to decompose your matrix into many parts to simplify the equations and solving of the linear systems. Think about matrix factorization that is used as part of the recommender systems, including the ones in the Netflix that uses the streaming company to recommend you movies when you go to the Netflix. So linear algebra is one of the most fundamental and must-to-know topics when it comes to mathematics for your data science AI journey. So let's now dive into the roadmap behind linear algebra and how you can learn linear algebra in 2024. I'm going to make use of the curriculum and the roadmap that we have carefully drafted as part of our 25+ hour Fundamentals to Linear Algebra course, which is also part of our Mathematics Bootcamp at lunartech.ai. So I'm going to make use of that roadmap, and I'm going to also make use of the applications of lunartech.ai in order to showcase you all these different topics as part of linear algebra roadmap of 2024. So let's dive in. First, we need to start with the linear algebra introduction. You will need to understand this concept behind linear algebra, where it is positioned in this entire field of mathematics, and why you exactly need linear algebra to study. So, first, you need to learn the prerequisites and all these must-to-know topics that you need in order to be able to understand linear algebra. Think about the real numbers, the vector space, this concept of the norm of a vector, the length of a vector, the Cartesian coordinate system, which is usually covered as part of the pre-algebra or algebra courses, and also the angles and trigonometry. Think about the cosine, the sine, cosine rule, the sinus rule, the tanh function, how it looks like when you visualize it, the geometric interpretation behind it, and also this concept of Euclidean distance and how Euclidean distance is different from the norm. And finally, you also need to understand this concept of Pythagorean theorem and the orthogonality. So when it comes to the linear algebra, one thing to keep in mind is that linear algebra is usually a course that is part of the undergrad studies like computer science, econometrics, advanced mathematics, advanced statistics, and usually the students of these studies, they in the second or third year of their bachelor, they learn linear algebra. And this roadmap that I'm providing to you is based on academic level plus the industry insights curriculum, which means that the concept is quite technical. So if you want to truly understand the linear algebra and you are serious about your career and your education, then this roadmap on one hand might seem a bit technical and intimidating, but on the other hand, you need to understand that students spend about a semester on this entire roadmap. But if you understand these concepts, this will open many doors for you. And instead of just using the libraries of people who have created, for example, large language models like the GPTs or the BERT or the mixtural AI models, instead of just using those libraries and pre-trained model, you can create your own models. And I think that's a good enough motivation for us to truly understand and invest the time and motivation to master the art of linear algebra. So once you have these prerequisites that usually come from pre-algebra or courses like the Calculus 1 and Calculus 2 to learn these different concepts, you are ready to go on to the first journey and first section behind the linear algebra, which is to learn the vectors and operations. So be prepared to learn the foundations of the vectors, the special vectors and operations, and let me actually go ahead and get more in detail curriculum for you. So start to understand the vectors and operations. What are the foundations of vectors? The fundamentals of linear algebra, the scalars and the vectors, this representation of the vectors in terms of the magnitude and the direction, and also understand this vector notation, the indexing of the vectors. First up, you can start with learning vectors and operations. So here you need to understand this scalars, the vectors, the representation of the vectors like the magnitude and direction, what is a common notation of the vectors in the industry, as well as this indexing in vectors. So understand what the indexing behind vectors are, because then you need to implement this in programming languages like Python. Then once you are clear on those topics, then you can get into the special vectors and operations. So understand what are the zero vectors and the unit vectors, the sparsity in vectors, the vectors in higher dimensions, the vector addition and subtraction, as well as the vector multiplication, so scalar multiplication, how you can calculate the multiplication behind the scalar and a vector. Also learn to the different properties of the vectors and the operations of these vectors. So once you are done with that, get into the advanced vector concepts. So learn the linear combination concept and try to understand this concept of unit vectors, the span of a vector, what is this definition and the application of it. The concept of linear independence is really important. Understand this concept and also be able to analyze and see from multiple vectors whether they are linearly independent or not. Look into this concept of scalar multiplication as well as the application of scalar vector multiplication, and look into this concept of length of a vector and a dot product, as well as what is the difference between the dot product and the inner product. After this, get into the topic of dot product, the Cauchy Schwarz and its application. So understand the concept of dot product, the inner product, what are the differences between the two, what is the properties of dot product, calculate the dot product by hand on many examples, and also learn this concept of Cauchy Schwarz. Cauchy Schwarz is an infamous inequality theorem, comes from linear algebra, and understanding its theory but also intuition, maybe you can even derive the proof of it using the cosine law, and how that relates to this concept of the norm of a vector, and when it is that the norm of a vector is equal to 0. So this completes then the vector operation section. In here, this is the high-level overview of the topics that you must know in order to learn the vectors and the operations. And once you are done with this, then you need to get into the next section and the domain in linear algebra, which is the matrices and solving linear systems. Here I'm talking about foundations of linear systems and matrices, the introduction to matrices, the theory and the intuition behind it, core matrix operations, Gaussian reduction, null space, com space, rank, and the full rank. So here think about the general linear systems like the coefficient labeling, homogeneous versus non-homogeneous systems, and what is this definition of matrices, the notation of it, as well as this concept of the rows, the columns, the dimensions of matrices, the identity matrix, diagonal matrix, other special type of matrices like ones matrix, the zero matrix, but also learn the core matrix operations and practice with them, like matrix operations of addition, subtraction, scalar multiplication, and also the multiplication behind multiple matrices. Once you are done with this, in terms of the solving of linear systems, think about matrix representation of linear systems, the solving of linear systems using the infamous Gaussian elimination, like understanding this augmented coefficient matrix, the row echelon form, the reduced row echelon form, the identity matrix, and the reduced row echelon form. Look into the detailed examples, implement this in practice with multiple examples step by step by manually deriving the solution to the system, as well as how you can calculate the null space, the com space, and the basis of these different spaces on an actual example. Once you are done with this, learn this concept of the rank and in what case you can say that the matrix has a full rank. Next up is the section of linear transformation and matrices. So learn the algebraic laws of matrices, their proofs, the determinant, the concept of the transpose, and the inverses of matrices. And here, this is exactly what I mean in more detail. So when it comes to the algebraic laws for matrices, learn about the commutative law for matrices, associative law, distribution law, the scalar multiplication law for matrices, and look into the proof of these laws as well as the examples. After this, get into the determinants and their properties. Look into the theory behind determinants, why we use determinant, how we can calculate the determinant on an example, as well as what are the properties of determinants and the geometric intuition behind it. So when it comes to the matrix inverses and identity matrix, look into the definition, the theory behind it, also this non-singularity of matrices, and what is this definition of and the formula when it comes to the inverse of a 2x2 matrix, and how you can go from there to a larger matrices, let's say 3x3 matrices. Look into the detailed examples, calculate them inverses of the 2x2 matrices in detailed examples, and also do the same for the 3x3 matrices. So how you can use this idea of conjugates and by changing these different signs to calculate the inverse of a 3x3 matrix. After this, get into the applications of inverses of matrices, why we need them, what is this intuition behind it, and where do we use it. Even when we are dealing with a very basic machine learning algorithm like linear regression, we use actually the transpose of matrices, the inverse of matrices, the multiplication behind matrices to find the solution to the linear system behind the linear regression. So this is a very important concept that I recommend you to learn before getting into machine learning. Next up is the transpose of matrices. Learn the properties of the transpose of matrices, the theory behind it, but also the implementation and the relationship behind the dot product. So once you are done with this, the next step is to get into a more advanced section, which is the final section when it comes to mastering fundamentals of linear algebra, which is this different advanced linear algebra topics. Think about vector spaces, the projections of vectors, the Gram-Schmidt process, the matrix factorization, and look into a couple of examples of matrix factorization techniques that are widely used across the industry, including the QR decomposition, the eigen decomposition, which includes the calculation of eigenvalues and eigenvectors, very popular topic as part of data science and statistical modeling, also AI, and getting to the singular value decomposition, which is the SVD. So let's dive into the details of this section. When it comes to the vector spaces, projections, and the Gram-Schmidt process, look into the definition of it, the step-by-step process behind it, the projection formula, and the step-by-step example behind the projection in order to truly understand how you can calculate the projection of a vector. And also look into the geometric interpretation and the intuition behind vector projections. Learn the theory, but also the implementation of the dot product of vectors and the dot product of a vector with itself. Look into the relationship between the dot product, the vector of the projection of a vectors, and then look into the concept of orthonormal basis. Understand the orthogonality, normalization, and look into the infamous Gram-Schmidt process. Understand how you can use the idea of dot products, but also the projections in order to conduct this Gram-Schmidt process step by step. Once you are done with this, then look into the application of Gram-Schmidt process and the orthonormal basis. So as part of the special matrices and their properties, I would recommend you to learn the special matrices like the diagonal matrix, the symmetric matrix, the orthogonal matrix, and the different applications and examples of them, step by step. Once you are done with this, learn this concept of matrix factorization. Matrix factorization is a very important topic when it comes to data science, machine learning, but also AI. The matrix factorization, different examples and techniques that are falling under this umbrella of matrix factorization techniques, they are used in both in machine learning, but also in deep learning and in generative AI. So if you want to become a true, well-rounded professional in these fields, then definitely be prepared to learn matrix factorization techniques. Dive into its applications, understand the different examples of what kind of matrix factorization techniques are used in what algorithms. And this will help you to get more excited and warm up for the next sections, which are detailed examples, and to truly understand at least a couple of matrix factorization techniques. So first up, learn, for example, the QR decomposition, which is a matrix factorization technique. Learn the theory behind it, the step-by-step process behind QR decomposition, how you can calculate the Q's and then the vectors of R. So construct the matrix of Q and then matrix R, and then decompose your matrix A into Q and then R matrices in order to decompose your entire matrix. Look into detailed example, the calculation of it with a step-by-step manual process, and look into its practical consideration and application in solving linear systems. After you are done with this, look into the concept of eigenvalue decomposition, how you can calculate the eigenvalues and eigenvectors, what is the theory, but also the practical implications of them. Where are eigenvalues and eigenvectors used, for example, in the infamous principal component analysis, so PCA. And then look into this concept of eigen decomposition, look into detailed examples, and manually calculate the eigenvalues and eigenvectors, as well as the eigenvalue decomposition. So once you are done with this and you have looked into the applications of eigenvalues and eigenvectors, the calculation of it, as well as the theory, get into the final topic, which is another matrix factorization technique, an infamous one, which is the singular value decomposition, the SVD. Look into the theory behind the SVD, the left singular matrices, the right singular matrices, the theory behind them, but also the practical example behind them. What is this idea behind singular value decomposition, how you can construct the matrix of S, the matrix of V, and the matrix of D, and how you can decompose a matrix into these three different matrices by constructing them separately. Once you are done with this, look into a detailed example. This might take a bit, let's say a half hour or 1 hour in the first go to calculate these different matrices by hand. But trust me, it is worth it, because you will then truly understand those concepts, and you will understand how and why those matrix factorization techniques are used and applied in data science and artificial intelligence. Welcome to the course on the fundamentals of linear algebra. My name is Date Vaslayan, and today we are going to start with some basic concepts that are important for understanding linear algebra. Linear algebra is one of the most applicable areas of mathematics. It is used by pure mathematicians that you will see in universities doing research, publishing research papers, but also by the mathematically trained scientists of all disciplines. This is really one of those areas in mathematics that you will see time and time again appearing in your professional life if you want to become a job-ready data scientist, or you want to do some hands-on machine learning, deep learning, and AI stuff. But also linear algebra is used in cryptology, it is used in cybersecurity, and in many other areas of computer science and artificial intelligence. So if you want to become this well-rounded professional, you want to go beyond using libraries, and you want to truly understand the mathematics and the technical side of these different machine learning algorithms, from very basic ones like linear regression to most complex ones coming from deep learning like architectures in neural network, how the optimization algorithms work, how the gradient descent works, and all these other different methods and models, then you are in the right place. Because you must know linear algebra such that you will understand these different concepts, from very basic ones to most advanced ones in data science, machine learning, deep learning, artificial intelligence, data analytics, but also in many other applied science disciplines. So before starting this comprehensive course that will give you everything that you need to know about linear algebra, first I'm going to tell you what we assume that you already know. Because linear algebra, it comes from about third year of bachelor's of different highly technical studies. And here we are assuming that you already know certain concepts. So to ensure that this course stays really on the topic of linear algebra and that you understand all these concepts really well, for that we need to be able to know different topics. So before we dive into these concepts, let's familiarize ourselves with the basic prerequisites and notations used throughout this course. And you will really need to know this in order to understand these concepts really well, such that instead of memorizing, you will actually just hear me once or maybe twice, and then every time you hear later on, or you see it in the papers or in some algorithms, you will recognize, this is something that we already learned. So some key prerequisites overview is here. First of all, to fully grasp the upcoming material, you should be familiar with some basic concepts like real numbers, vector spaces. So you don't need to know this idea of vectors, though you already most likely are familiar with this, given that you know how to plot different lines, you know the idea of x's and y's and how to plot these different graphs. But here we are going to touch base on this every time when we come close to these concepts. I will refresh your memory, and we will go through these numbers, the idea of norms and distance measures. because when it comes to the vectors, when it comes to the magnitude and all these different topics that we are going to discuss as part of linear algebra, knowing what norm is and what is the definition of distance, what is the length between 2 points when we plot it in the 2-dimensional space or 3-dimensional space, those are all very basic concepts that usually you see as part of a basic pre-algebra or just common algebra courses and lessons. In order to truly understand what linear algebra is about, to understand this direction of vectors, the angle, and then the dimensionality reduction, how linear algebra is applied, for instance, in different algorithms in machine learning, deep learning, data science, statistics, you really need to understand this Cartesian coordinate system. So this is not only important for linear algebra, but I assume you already know it given that you have passed those other courses like calculus, or usually they are covered as part of pre-algebra or algebra. So the Cartesian coordinate system, I mean here understanding what is, for instance, the common description of them. For instance, when we write like x and then y on the vertical axis, and then we have here 0, and then we can always plot these different plots. We have a clear understanding what is this y is equal to x line. We understand how by knowing certain points we can plot different plots. For instance, that this is the y is equal to x line, that here it means that if we have here 1, then this is just 1, 2, this is 2. So we understand when we have the function of the line and we have a certain value, whether it's our y coordinate or x coordinate, then the corresponding coordinates can be found. Then you also need to know some basic things that I just didn't mention right now. So for instance, that the numbers here can be like 1, 2, 3 up to infinity. So you understand this concept of infinity, and then here the same story. Then here we have -1, -2. And then this is then used later on, and we will be touch basing this when we will be describing our vectors and how we can visualize our vectors in a 2-dimensional space like we have here, because this is 2-dimensional, so we have x and y, but we can also, of course, visualize it in 3-dimensional, etc. So this idea of basic coordinate system is really important, usually covered as part of algebra, if not pre-algebra. Then we have basic geometry, which means that you need to have a clear understanding what sinus is, what cosine is, what tangent is, and their reciprocals. And here I mean that for instance, what is cosine function, what is sine function, that you have an understanding, for instance, that what is this line, whether it's a sinus line or cosine line. You have also an understanding what this pi is. One thing that I didn't mention, but it just goes around all these topics, some basic things that you understand what is x, what is y, why we use them, and this idea of variables. And also you need to understand this idea of a square or, a 90-degree angle, and then Pythagoras theorem. Here we have the same. So what is this relationship between different sides of a triangle that is a very unique triangle, and that has one of the angles as 90-degree, and this idea of the sides, how this relates to the sinus, cosinus, tangent, cotangent, and also how the Pythagorean theorem applies when we have a triangular, but it is no longer with an angle that is 90-degree. What is the sum of all the angles of a triangle? So those are basic stuff that are commonly covered as part of trigonometric lessons or part of general geometry. So when it comes to this R, so as part of real numbers and vector spaces, R represents the set of all real numbers. So you can be dealing with, for instance, an integers like 1, 2, 3. This will also cover all the negative numbers like -1, -2, -3, but also the floating numbers like 1.223 and all the other numbers that you can think of. Those are the set of all real numbers. So this is in one-dimensional space, right? So you can see that I'm writing just one number, 2, 3, and other numeric numbers. Then we have the idea of R2, R3 up to Rn, where all these numbers, they represent, in this case, the n. It represents the n-dimensional Euclidean space. So when it comes to this idea of n-dimensional numbers, so for instance, R2, here we just mean 2D plane. So I'm pretty sure you are familiar with this idea of, for instance, x-axis and y-axis. Here we are dealing with two-dimensional plane. So for every point that we can find here, we can describe them by assigning them a value x, so coordinate x, and a coordinate y. That's exactly what we mean by saying that the number can be represented in a 2D plane. So here we are dealing with this two-dimensional space. This is our two-dimensional Euclidean space. And every number in here that is part of this R2 can be pictured here, can be represented in this visualization. So for instance, if I have this number, and let's assume that the value on the x-axis is 2, and we can see here that the corresponding y is 0, I can describe this number, which I will call a. I can describe this by writing down first the x-coordinate, which is 2, and then the y-coordinate, which is 0. So I'm then saying that a, which is a point with x-coordinate 2 and y-coordinate 0, it is part of my R2. And it's part of my two-dimensional Euclidean space. When it comes to R3, similar thing we can do with that, only in that case we need not just x-axis and y-axis, but we need to add our third dimension. So here, for instance, when it comes to the R3, then we need to do y-axis, we need to have x-axis, but also we need to have some z-axis. So, such that every time, every point in the space, we can then describe by x, y, and z coordinates. So if we write it in terms of the vector, something that we will see very soon as part of our first unit of this course, we will then need to represent every number in this three-dimensional Euclidean space by writing down first the x-coordinate, let's say 1, and then y-coordinate, let's say another 1, and then z-coordinate, which is 1. Or even better, even easier, let's use 0, 0, 0, which means that we are dealing with this initial number, which is the center of this three-dimensional Euclidean space. When it comes to the n-dimensional or the higher dimensional spaces, it's much harder to visualize. Therefore, usually when it comes to visualizations, we usually only visualize the one-dimensional, two-dimensional, and three-dimensional spaces. Above then, it just no longer does make sense to visualize it. But we definitely deal with them, and they are part of applied linear algebra. So understanding the spaces is very important for analyzing vectors, for their interactions, and this holds not just for this two-dimensional and three-dimensional, but really for multi-dimensional spaces. Let's now quickly define this idea of norm. So the norm of a vector denoted by this v, which you can see kind of like similar to the absolute value from pre-algebra. You can see here that we have this double straight lines like from absolute value. And then we have the name of the vector or the variable name that we are assigning to our vector. And then you might notice here on the top of this arrow. This basically says that we are dealing not with just a variable, but really we are dealing with a vector. This is really important because you can see that there makes a huge difference if we have, for instance, just v or v1, I have to say, or just v. Those are really important and things that you need to keep in mind when it comes to linear algebra and trying to differentiate vectors from a point. You will notice that when it comes to norm, we can represent it either by this notation or this. Usually it's a common notation in machine learning or in data science with this 2 bars. And when we do this, we automatically also know L2 norm. And this is something very common and usually used as part of retrogression, which is an application of linear algebra, and it's used in regularization. So we are regularizing our machine learning algorithms. So when you get into machine learning, you will see time and time again this notation. So next time when you see this, then you know automatically that you are dealing with L2 norm. And L2 norm, which is also used a lot in machine learning, it is referring to the usage of L2 norm in the retrogression. And retrogression or L2 regularization is a very popular regularization technique as part of machine learning. So right now, even you can see this intersection of linear algebra or this idea of norms in machine learning. The norm of this vector v is equal to square root and then v1 squared plus v2 squared plus and all this in between numbers plus vn squared. So here basically it means take the square root of v1 squared, then v2 squared, plus v3 squared, blah, 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 plus vn squared. So basically, take all the units that form this vector and then, so are on this vector, and use them, square them, and then add them, and then take the square root of that. That's the distance, or I have to say the norm of this vector. We saw already the norm. Here is just another example what the norm is, and on a specific 2-dimensional vector, when we have, for instance, that the vector is equal to 3 and 4, which means for the first dimension, let's say on x-axis we have 3, and then on y-axis is equal to 4, then the norm, so this is equal to, we take the x value, so 3, and then we square it. So v, you can see here, this is the case when n is equal to 2. This is simply equal to square root of v1 squared plus v2 squared. And as v1 is equal to 3, so this is our, maybe I can make this just v1, and this is my v2, then the norm or the Euclidean distance for this vector, so this thing is equal to v1 squared plus v2 squared, which is equal to 3 squared plus 4 squared. And this value is square root of 25, and it's equal to 5. So let's now see the difference between Euclidean distance and the norm. So you could see here the norm. Here we have just one vector, like here. And this norm, it has just 2 corresponding values in the 2-dimensional space. You see here we have just 3 and then 4. So this is v1 and v2. When it comes to the Euclidean distance, this is kind of the generalization of this idea of norm. So the Euclidean distance between 2 points A and B in Rn, so in the n-dimensional space, is the norm of the vector connecting A to B. So we see that the norm and the Euclidean distance are highly related to each other, only we are talking about the norm when it comes to one vector, but when we have this vector A and the vector B, this is simply the Euclidean distance. So for the Euclidean distance, we know already this idea of distance, how we can measure it, and you can see that this comes very similar to what we see here. Notation, and here we are saying, well, we have this vector, and then it has these 2 coordinates in n is equal to 2 in 2-dimensional space. When it comes to the Euclidean distance helps you understand what is this distance between 2 points in an n-dimensional space. So the Euclidean distance between 2 points, let's say A and B, in n-dimensional space is the norm of the vector connecting A to B. So for instance, if we have a point A and we have a point B, we are connecting this, and this is the vector connecting these 2 points, then the Euclidean distance is simply the norm of this vector. So this is the Euclidean distance. So we can see that the norm and the distance, they are highly related to each other. In the Euclidean distance, we are using this idea of norm, and specifically the norm 2, as I mentioned before. So here you can see that the definition of Euclidean distance, so the distance between A and B, those 2 points, is equal to square root of A1 minus B1 squared plus A, and then here we have basically A2 minus B2 squared, and then plus A3 minus B3 squared. Those are things that we cover as part of this ... and then plus up to the last point when we have an minus bn squared. So here what we mean basically is that if we have 2 points, here is A and here is B, and this is our vector, and we know all these different points, so A1, B1, A2, B2, A3, B3, blah, 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 and then here AN, BN. We know all these points lie in here, in this distance. Then we are taking them and using them to calculate the Euclidean distance. So here, for instance, if we have point A and B, so in this example, let's do a quick one, specific example when we have a point A which has coordinates 1 and 2. So this is basically A1, A2, and then point B with points in it like B1, B2. You can notice that the DAB, so the distance or the Euclidean distance of these 2 points, which is equal to the norm of this vector. But here this is A and this is B and this is this vector. This is equal to square root of 4 minus 1. So it takes the B1. So this is B1. And this is A1. Takes the square and then says plus B2 minus A2 squared. Takes the square root of that and says this is equal to 5. Now, you might be wondering, but hey, why do we do then, instead of 1 minus B1 squared, we do B1 minus A1 squared? And the answer to this question lies in the properties that we learn as part of pre-algebra. Because it doesn't matter when we take A1 minus B1 squared or B1 minus A1 squared. Because this squared ensures that it doesn't matter which one we take first and subtract the other. Now, the proof of that is outside of the scope of this course. This is part of pre-algebra, but I just wanted to put this out there to ensure that you are seeing what we are seeing here, because here it says A1 minus B1, but in this example we are taking instead the B1 and we are subtracting A1. This is a common thing that we do in pre-algebra and just in general in different Euclidean distance or distance related cases. So I just wanted to put this here to ensure that later on this is something that can be clear from the first view. So why this is important, this idea of norms and Euclidean distance, beside of being used in machine learning, and why is it used? So norms, they provide a way to measure the size or the length of a vector in vector spaces, which means that when we want to measure a distance, a similarity, a relationship between, for instance, vectors, then it becomes much easier to use this idea. And Euclidean distance is not only used in regularization techniques like L2 regularization or retrogression, but it's also used in other machine learning or deep learning algorithms as a way to measure the distance or the relationship or the similarity between two different entities. Those can be variables, those can be two people that we want to compare in our algorithm, or two entities. For instance, the norms or the Euclidean distance, they are also used as part of K-means algorithm, something that you might have heard. And if you follow later on the machine learning and the clustering section of machine learning, you will see that Euclidean distance is used as part of K-means algorithm that aims to cluster observations into different groups. So this is also yet another highly applicable topic that you must know in order to understand different linear algebra topics, but also machine learning topics. Why these prerequisites matter and why I mentioned those. Understanding these concepts is very crucial. They underpin this geometric interpretation of linear algebra. They will help you to better understand these concepts and not just to memorize them, but really understand. And later on, when you go into your machine learning and AI journey and in your data science journey, seeing these concepts will help you to better understand those different algorithms, these optimization techniques, what we mean when we say we want our optimization algorithm to move towards local minimum, global minimum, this idea of movement, this idea of vectors. Later on, you will also understand these different concepts in deep learning, how these models work, how the neural networks work. And those are essential concepts that you need for solving different systems of linear equation, a core part of this course. They also help you in visualizing vector spaces, which are critical to understand this concept of linear algebra, the applications of linear algebra when it comes to the real-world applications. So those are things that you can definitely master by following some of our other courses. But for this course, I assume that you are already familiar with these concepts. Right. So now we are ready to actually begin. And with these prerequisites in mind, you are prepared to start your linear algebra journey. We are going to learn everything in the most efficient way, in such a way that you will learn the theory. You are going to see many examples. We are going to learn everything in detail, but at the same time, you're going to learn the must-know concepts, and I'm not going to overwhelm you with these most difficult concepts that you will not be seeing in your career. I'm going to give you this bare minimum when it comes to really knowing and the must-know for linear algebra, such that you will be ready to apply linear algebra in your professional journey, whether you want to get into machine learning, deep learning, artificial intelligence, data science. Knowing these different concepts in linear algebra, you will be a pro in your field. I'm going to give you everything that you need, the theory, examples, implementations, everything in detail, but at the same time, you will be doing that in the most efficient and time-saving way. So without further ado, let's get started. Hi there. So let's get started with our first module, which is Foundations of Vectors. In this module, we are going to talk about fundamentals of linear algebra, vectors. We are going to make a differentiation between scalars and vectors. We are going to define them. So first we will learn the theory, then we will implement them into practice by plotting them, by looking into different examples. Then we will look into this representation of vectors by looking into the magnitude and the direction of it and the representation of them just in general. We are going to plot them in our coordinate system. Then we are going to see the common notation of vectors and the indexing of them. Vectors are super important when it comes to linear algebra and application of it, and they matter not only in mathematics but beyond. So vectors help us in many ways, from figuring out how objects move to solving math problems in science and just in general in technology, including in data science, machine learning, artificial intelligence, etc. They are super useful too. So let's start our journey with looking into scalars. So scalars, they are just plain numbers. And by definition, a scalar is a single numeric value, often representing magnitude or quantity. For example, scalars can be describing the temperature outside. For instance, the temperature of 22 degrees can be represented by a scalar, or a height of a person can be represented. It's a scalar. So let's assume we have a scalar that we will define by a letter S. It's just a variable. This scalar is then equal to 22, for instance, and we are measuring it in degrees. So it means that if this S measures room temperature, then the scalar S, which is equal to 22 degrees, it represents the room temperature. It can be, for instance, 18 degrees or 9 degrees if it's very cold. It just measures a single value. It represents just a single number. Or it can be, for instance, 17, 100, 2.22. So all this, they are just scalars. They represent a single numeric value. They often represent the magnitude or a quantity. Very soon we will see that scalars, they are a value that represent the magnitude of a vector. So now when we are clear on this very basic concept of scalars, let's actually move to this idea of vectors. So by definition, a vector is an ordered array of numbers which can represent both magnitude and direction in space. So vectors, they are a bit more. They represent a bit more than scalars. They are numbers that also show direction, like a car speeding down the highway or a ball being thrown. For instance, when it comes to our previous example, where we were using this room temperature as a way to think about the scalar, a scalar, for instance, scalar that we just saw was this room temperature, which was 22 degrees. When it comes to the vector is different. For vector, for instance, we can have an example when a bird, for instance, it flies at 10 kilometers per hour. And I also add here another information which will make this as a vector, which is that it flies south. So here, as you can see, what I'm doing is that I'm not just, let me actually remove this part to make it easier to understand. Okay, so in this example, let me write it down that the example bird flies south at 10 kilometers per hour. So you can see that I'm not just adding the scalar, which is in this case the magnitude. We will see very soon the formal definition of it. So I'm writing down the speed, I'm defining the speed, but also the direction. So I'm saying I know that the bird is flying south, that's the direction, and I know also the speed of it, which is the magnitude, so 10 kilometers per hour. So here, in the vector, I have much more information than in the scalar, because in the scalar, I just got temperature, room temperature, single value, but in case of a vector, I not only have magnitude or speed, like 10 kilometers per hour, but I have extra information, which is the direction of it. For instance, flying to the south. So let's now look into some real examples and plotting them to make more sense out of this idea of vectors and what is this magnitude, what is the direction. So let's assume we have a 2D plane. So we have x-axis, we have y-axis. Here, like usual, we have our 0, 0 center. And we want to plot a simple vector. So usually the way we represent vector in tutorials or just writing down is by writing the name of the vector. This can be just a random name. And let's assume that it's a V, letter V. And then on the top, we are always adding this arrow. So this arrow, it says, and it tells the person who is reading that we are dealing with the vector. Arrow on the top is that reference. So let's assume this vector V, it starts from the center of our coordinate system and it goes to this point. So let's say in here, this is our vector V. So let's assume that this point in here is equal to 4, which means that the x-coordinate is 4 and the y-coordinate is 0. As the arrow, it just, as the point in here, it has a y value of 0. So you can see that it goes straight from 0 to this one, to this point. Okay, so what tells this vector to us is that we have a value that describes the length of the vector. So it goes from 0 to 4, which means that the length is equal to unit 4. So it's equal to 4. And we have just learned, and we were just talking about that the magnitude is the length in this case. So the length describes the magnitude in this case. So this means that the magnitude of this vector is equal to 4. And then what else we can see here? We can see the direction of the vector, which means that the direction is also something that we can see here. This is the direction of the vector. So this, going straight from this point to this point in a horizontal way. So independent whether I plot this vector from 0 to 4 in here, or in here, or in here, or in here, or in here. In all cases, as long as the length is this, I'm dealing with the same vector because I am basically in this entire R2 space, I have exactly the same vector. All I care is about the magnitude and the direction. Where will this vector start and where will it end? I am not interested. I'm interested that the magnitude, in this case the length, is equal to the direction of the vector. So let's now look into another example where we go a bit more difficult on our coordinates and on our vector. We already saw that we had this vector where we went, let me change the color. So this was our vector v, and it went from 0 till 4. So this point, to be more specific, is, so this vector, the vector v, it goes from 0, 0 to 4, 0. So the coordinate x was 4 and the y was 0. Now let's plot another one where the direction is no longer horizontal for this vector. Let's call it vector w. And for this vector w, we will again start with 0, 0. So we will start again in here. But this time, we will go a bit like this. So let's say we go all the way to this point. So this point has a value for in x-axis of 3, and for y-axis it has a value of 4, which means it goes from this point to this point. And this is the direction of our vector v. So it goes to 3, 4, because this point is 3, 0, and this point is 0, 4. So x-axis is 0, x-coordinate, and y-coordinate is 4. So now you can see that the direction of this vector is like this, while the direction of the vector v was like this. And like in case of vector v, I again no longer care about where exactly my vector w starts and ends, but all I care is about its magnitude, so the length and the direction. So, for instance, I can have the same vector in here, the same vector in here. As long as the length, the magnitude is the same and the direction, I am dealing with the same vector. That's all I care. So the magnitude and the direction is all that you care about. All right, so now about the length. That's something that you can see very easily from this specific example, because by using the Pythagoras theorem or Pythagorean theorem, we can see very quickly that as the length of this side of our right angle is 30 degrees. So right triangle, we can see that this side is 3, this side is 4, which means that this side is 5, because 4 squared plus 3 squared, then we take the square root of that, is square root of 25, and it's equal to 5. So the length or the magnitude of this vector v is simply equal to 5. All right, this was about this specific vectors. Let's now look into the common representation of the vectors. So we always use the magnitude as well as the direction in order to represent the vectors, and they commonly are represented by two different ways. Let's now look into the first way that the vectors can be represented, and then we will move on to the next one. So when it comes to the vector v, so we saw that vector v was moving from point 0, 0 till to the point of 4, 0. So we can represent the vector v by 4 and 0. When it comes to the vector w, we can represent that vector. So vector w, we can again do the parentheses, and we can say that it's equal to 3, 4. So by using the coordinates from the coordinate system, we can then represent our vectors. So this is just one way of representing a vector. Another way of representing these vectors is by using these square braces. Given that we are in the two-dimensional space, first we will mention here the 4, then we will mention the 0. In here 2, So we can say 3 and 4. This is yet another way of representing the vectors in a two-dimensional space. So if we were to have a three-dimensional space, so let me actually show it on a new page. So if we were to have vectors in three-dimensional space, so we are dealing with R3. So we have points that can be described by x, y, and z. So coordinate space like this. So x and then y and then the z. Then every point, so let's say we have this vector, then we had to represent it by a value, let's say x1, y1, and z1. Or better, let me actually use a different letters, A, B, and C. And this would be my vector V. And I could also represent this vector V, it's the same, so vector V can be represented as A, B, and C. So one thing that you can notice is that unlike the R2, now I have 3 different entries, what we are also referring as rows. And we just got 1 column. So we can often represent, and usually that's a common way of representing vectors, by using these columns. So columns help us to represent our vectors. And you can see very clearly then when it comes to the two-dimensional space, so when we have R2, so then our vectors have just 2 rows. So 3 and 4, 4, 0 like in here. When it comes to three-dimensional space, we have 3 entries, and so on. So the same holds, of course, also for instance, R5. Then for R5, our vectors, so coordinate space can be, for instance, x, y, z, and then gamma, and then let's say delta. And then the coordinates of a vector in that space can be v, and then arrow is equals to, and then we would have, let's say, A, B, C, D, E. You get the idea. So depending on the space, the coordinate space, and the dimension of that space, then the corresponding vectors can be represented accordingly. So the vectors are quantities that have both magnitude and direction, as we just saw, distinguishing them from scalars, which only have magnitude. So we saw that the scalars got only magnitude, while in case of vectors, we saw both for the vector v and for the vector w, we didn't only have the magnitude, so the length of the vector, but also the corresponding direction. So when it comes to the vectors, so this is exactly what we just saw in our example, a vector in a two-dimensional space, so in R2, can be represented by using these square braces and the corresponding entries for x and y, where x is basically the x coordinate in our coordinate system. So in our x and y system, whenever you have this x and y coordinate, then this x coordinate will then describe your magnitude, and the y coordinate will then describe your second entry that you need to put when representing your vectors. So here the x and y indicate the movement in the horizontal and in the vertical dimensions respectively. So for the x's, it's always the x coordinate, so how far you move towards the horizontal direction in here, or independent in here. So always take the x coordinate, that is the value that you need to put first, and then the y need to be put it in here. So indexing in vectors. When it comes to the indexing, the standard mathematical notation indices in the n vectors goes from I is equal to 1 to I is equal to n. So the notation here can be a bit ambiguous. So AI could mean the ith element of AI, the A vector, or the ith vector in a collection. So let's start with a simple one and then move on to this next part. So what this means and what this means we will look into now. So usually when we have a n-dimensional space, we are having hard time visualizing it. Therefore, we use this two-dimensional space or maximum three-dimensional space in order to get an understanding of what these vectors are. So we just saw examples of them when creating our vectors in V and W in R2 and also in R3. But we can have similar vectors also in R4, in R5, or all the way down to Rn, where n can be 100, 200, 500, any number as large as you want. The thing is that visualizing R4, R5, Rn is very hard, but we can still benefit from these great properties of the vectors, matrices, and in general linear algebra in order to describe different things that have more than 3 dimensions. Therefore, we have this bit more ambiguous notation where we use Rn, and this n can be any real number, and it can be all the way to infinity, so very large number. And let's say we have a vector in this Rn, then this vector is usually described by using similar square brackets like before, only with more entries. So like before, we got just one column, so that's something that we didn't change. But here we have, instead of just 2 entries or 3 entries like in the 2-dimensional or 3-dimensional spaces, now we have A1, A2, A3, all the way down to AN-1 and AN. So we got in total n elements in our column, and this describes our single vector. So this vector in an n-dimensional space. This we can call also A. So one thing that we just saw is that it was saying in our definition and notation that we might also be dealing with the each vector in a collection, which means that sometimes you will see this, while here the A1, A2, they are vector themselves. So here we saw that these are just entries. So A1 is a number, A2 is a number, A3 is a number, AN is just a number. But it's also possible when you have a much more difficult and complicated case that you got an A, let's write it down with a capital letter A, which is equal to A1, or let's actually remove this. So we got, let's say, A1, A2, A3, all the way down to AN-1 and AN, where you can already see what is going on. So instead of having just a number as an entries, instead we have vectors in here. So our first element is actually vector, our second element is actually vector, so A2 arrow, A3 arrow, all the way down to AN arrow. So while here, this can be, for instance, some numbers, let's say 1, 1, 1, all the way down to 1, 1. Here, we have a vector, vector, another vector, and all the way down here, yet another vector. Where, for instance, when we remove this part, where, for instance, A1 arrow is actually equal to A11, A12, A13, all the way down to A1n. One thing that you will notice here is that, unlike in here I got double indices. So I got here A11, and then A12, and then A13, all the way to A1n. So the first index, it doesn't change, as I have here a 1. So I'm writing down the index corresponding to this vector, but the second index, it changes per entry, indicating which element specifically in the vector I'm talking about. So from the first index, you can identify the vector that I'm referring to, which is A1, and from the second index, you can see the corresponding entry or the value that element is positioned in this vector. So you can see that this value is, for instance, in the vector 1, so A1 to be more specific, but then it is in the first position, this is in the second position, in the third position, all the way down to the end position. So And this is something that is really important to understand well, because this notation is going to appear time and time again across various applications of matrices and vectors. So it is really important to understand well. Therefore, I want to go one more time through this to make sure that we are clear on what these indices represent. So whenever we have an index, a vector that we want to represent, and it is just a vector, which means that it's not a nested vector in a vector, then we can define it by, let's say, A, and then on the top an array, and it's equal to, and here we can have A1, A2, all the way down to AN. So you can see what we are also referring as dimension of this vector is equal to n by 1. So I got n entries and just one column. So n by 1. Which means that this already gives me an indication that most likely this A1 is a number, this A2 is a number, this AN is a number. So let's say this is equal to 1, 2, 3, blah, blah, blah. And then here I have, let's say, 100. But if I'm dealing with a nested vector, later on we will see that this can be represented by a matrix. Then I can also define this by capital letter A, which is a common way to refer to either matrices or nested vectors. And then this is equal to A1 arrow, A2 arrow, A3 arrow. This already sends a message to the reader that we are dealing with no longer constants within a vector, but rather vectors in a vector. And what can we see here is that the dimension of this nested vector, or which we can also refer to as a matrix, here the number of rows, so the number of entries, these elements, we can see it's equal to n. But then this time, the number of values that form these vectors is no longer 1, because we are not dealing with just a constant. This is not some constant, but rather this is yet another vector. So let's assume this vector has a length of m. So let's say this has a length of m. Then the dimension of this matrix A is equal to m. So something that we will see also when talking about matrices. So let me actually clarify this bit more. For better understanding, let's say we look into one of those, one other example of an entry. So let's say we look into this specific vector, which is in the third vector within this vector capital A. So this A3 vector. So one thing to see here already is that I assumed that these vectors, they got m elements. And keep in mind that all these vectors, they should be of the same size. So it means that I already know that this specific vector A3 has m elements. So m elements. So I'm representing this A3 vector from here. I'm taking this out from this entire nested A vector, and I just want to represent this. And now, unlike these elements that got an arrow on the top, this time I will have constants forming the A3 vector. So I no longer have vectors, but I have elements in it. So in here I will have A, let me actually write down all the A's. But to refer and to make sure that I recognize that I'm dealing with the third A vector, so A3 arrow, here I will put 3, all the way here 3. So they all come from the same third A3 vector, but then their positions is different because this is, let's say, 1, 2, and then all the way down to mth position. So these indices help us to keep track what are the position that these values are taking part in the vector A3 arrow. This might seem a bit complicated at the moment, but once we move on to a bit more complex material like matrices, it will make much more sense. This is a bit of an extra. I just wanted to showcase this, but this is what is at its core and what you need to understand at the moment. To understand this concept of vectors, so you need to know that vectors can be represented by this arrow on the top. So let's say vector A, and it has, let's say, n elements. Then you can write these square brackets, and then you will need to mention A1, A2, all the way to AN, which means that you have n different entries describing your vector. So you have A1, which is the first element in your vector, A2, the second element, all the way to AN, which is the end element. Where here you can see, for instance, so if I add here A3, that A1 is simply equal to 1, A2 is equal to 2, A3 is equal to 3, all the way to AN is equal to 100. So these numbers, I'm basically taking and I'm representing them and putting them in here within square braces in order to get a representation of my vector. So my vector A has all these different entries, n different entries, and it starts with 1 and it ends with 100. This is a vector. And then when it comes to the vectors within vectors, here we need to be a bit more careful, because here we not just have constant values forming a vector, but we have vectors that form yet another vector. So our vector A, our nested vector A, which we later will refer as matrix A, has actually entries that also are vectors. So we have A1 vector, A2 vector, A3 vector. They are not just constants, but on their own they are vectors. So here, for instance, we have defined also an example of it. We have said, let's look into this third specific vector that is part of A, which is A3 vector. And that one has m different elements. Here we have then the index referring to the which vector from the nested vector A it is, which is the third one, because we have taken it from here. But then on its own, this vector has different members, m different members to be more specific. Therefore, we have also an index to keep track of the position of this value, 1 to up to m. And this can be yet another, this time it can contain some elements, an example of which is, for instance, 0, 1, 2, all the way to, let's say, 500. And this can be different numbers. It doesn't need to be ordered. It doesn't need to have a specific pattern. They can be just random numbers describing this A3 vector. So hopefully this makes sense. If it doesn't, don't worry, because we are going to see this time and time again. I just wanted to give you a brief of an intro such that you can remember this when we come back to a bit more complex topics like indexing in matrices. So now let's talk about special vectors and operations. Here we are going to talk about zero vectors, unit vectors, the concept of sparsity in vectors, as well as vectors in higher dimensions, like we just saw about this n-dimensional space. We will also talk about different operations we can apply when it comes to vectors, like addition, subtraction, and then later on in the next module, we will also talk about multiplication. We will also be looking into the properties of vector addition after we have looked into some detailed examples when it comes to operations on vectors. All right, so let's start with the zero vectors and unit vectors. When it comes to the zero vectors, you can see here already that the zero and arrow on the top, it basically refers to the vector, like we saw before, only with the difference that all its members are 0. So you can see here that we have 0 and then an arrow, and then underneath here we have some number 3, and then this is described by this common representation with the square braces and then 3 different members, 0, 0, 0, so all 0. And then it says in R3. Okay, so why are we doing this? Well, when it comes to different linear algebra operations, sometimes we just need to add zero vectors, or we just want to create zero vectors. It's just easier to work with. We want to just create an empty vector. We know the length, but we want to keep it empty such that later on we can add something on the top, or knowing that when we add a 0 on a number, the number stays the same, we can make use of this property to do different tricks when it comes to programming in Python, in Scala, or in C++, etc. So therefore, this idea of zero vectors can become very handy. Now, one thing that you need to notice here is that we are not just writing it down, this zero, to emphasize we are dealing with a vector, but like before, we have this arrow on the top, emphasizing that we are dealing with a vector. Then what we are doing is that we are also adding the dimension of this vector. So in what dimension, in what space are we creating this zero vector, that this vector is located? Is it in R2, in Rn, in R3? In this specific case, you can see that in this example, the index that we got here is 3, which basically indicates we are dealing with a zero vector in 3-dimensional space. So in the R3. In general, we would just note this by n, keeping the notation general, which means that we are dealing with 0, 0, all the way down to 0. So it has n by 1 dimension in Rn. All right, so this is about zero vectors. It is just a way to make our programming life easier, also to use it in different algorithms when it comes to a bit more advanced algebra. The next type of special vectors that we will look into is this unit vectors. So vectors with a single element equal to 1 and all the others 0, denoted as EI for the ith unit vector in n dimensions, are referred by unit vectors. So what we mean here, when it comes to the unit vectors, if we have, for instance, E1, it means that we have a vector where the ith, in this case, the first element is equal to 1. So you can see that E1 is equal to 1, 0, 0. So in the first element, we got 1, and the remaining is 0. And this is really important that we are dealing with vectors that contain only elements of zeros and ones. And the only member that is equal to, the only element in that vector that is equal to 1 is the ith element in the entire vector. All the remaining ones are 0. And you can see here that the dimension is no longer specified, but just the index of the entry where the 1 is located. So let's look at another example. In here, for instance, when it comes to the unit vector, yet another unit vector is E2, which basically means that in the second element, so in the second place, the vector contains 1 and all the other members are 0. So here you can see 0, here you can see 0. Only in the second element we have 1. And then in the E3, what we have here is that the third element is 1 and all the other ones are 0. So let's actually look into one bigger vector in higher dimension to make it even more sense. So first I will define and assume that we are dealing with a vector in Rn, so in an n-dimensional space. This gives me an idea that we are dealing with. So we are not dealing with a nested vector, we are dealing with a simple n-dimensional vector. So it has n rows and 1 column. So using the square braces, I'm going to represent my vector. So I have all these different members, n members. C, so E, let's say it is E5. So what does this mean? It means that I is equal to 5. And this ith element, so the fifth element, is equal to 1. And all the other entries, the elements in this vector, are zeros. So let's look into this is 0, 0, 0, 0. I'm approaching the fifth element in my vector. So it's this one, this is 1, and the remaining all zeros. So this is a unit vector in an n-dimensional space, and I'm defining it by E5 because my fifth element is equal to 1. Now those are very handy when it comes to some other techniques in linear algebra and just in general. Think about techniques like row echelon form, solving linear equations, something that we will see as part of the next unit. So many things we can do by using unit vectors. Unit vectors are super important, so you need to understand this concept very well, such that later on you will understand more advanced concepts in linear algebra. Let's now look into the topic of sparsity in vectors. So by definition, a sparse vector is characterized by having many of its entries as 0. So its sparsity pattern indicates the position of a non-zero entries. So what we are basically saying is that if we are dealing with a vector that contains too many zeros, we are dealing with a sparse vector. So this sparsity pattern indicates also the positions of a non-zero elements. So if we have unit vector, it means that we are already dealing with a sparse vector. This is a concept that is super important when it comes to linear algebra, but also in general data science, machine learning, and AI, because having a sparsity in your vector, it means that you don't have much of an information. Usually a value 0, it means you don't know much about that specific value. And if you got just too many of zeros and too few numbers, which do provide information, it means that you are dealing with a vector that doesn't provide you much information. And there's always a problem when it comes to data science, machine learning, and AI. So sparsity is something that you need to be aware of. You need to know how to recognize it. And you also need to know whether there's a problem in your specific case or not. So let's look into an example. Let's say we are dealing with this vector x that has 5 different elements. So x is a vector coming from 5-dimensional space. So we have, for instance, an element of 3 in the first entry, then we have 0, 0 in the second and third entries, then we have an entry 4, which coincidentally also contains value 4, and then the last element in our 5-dimensional vector x is equal to 0. Now, what do we see here? We see that the majority of elements of a vector x is equal to 0 because we got in total 5 elements, and then we got 3 of it actually being equal to 0, and only 2 of them containing information like equal to 3 and 4. So only 2 elements that are not 0, so non-zero elements. It means that 3 divided to 4, which is basically 60%, 60% of all the entries in the vector x are equal to 0. So the 60%, it means that is above half, so above 50%. 60% of all the information in this vector, the majority is simply equal to 0. This type of vectors we are calling sparse vectors, and sparsity is really important concept that we need to keep in mind later on. So while we can visualize vectors in the 2 and 3 dimensions, in linear algebra, like we just saw in case of these n-dimensional vectors, visualizing this type of higher dimensional vectors becomes very difficult. So this mathematical flexibility to work with this type of information, so when we can represent information with many entries, we can represent it by vectors, which we can actually not visualize, becomes very handy for complex data structures, for different simulations in physics, and much more. So we just saw in a couple of examples how we can represent vectors in a high-dimensional space using this square braces and this common vector notation representation. We saw that in an n-dimensional space, we could very easily represent this very large matrix or vectors by just using this vector representation. For instance, if we got a vector that had n different entries, where n is, for instance, 1,000, so let's say we have 1,000, then we can represent this vector or this information by using common vector notation. So A1, A2, all the way to A,000. So, of course, we cannot visualize this. It just doesn't make sense. We can visualize 2-dimensional vectors. We can visualize 3-dimensional vectors, but we cannot visualize 1,000-dimensional vectors. So, a vector that comes from R,1000. But what we can do is still make use of this very useful information in order to do different operations. And later on we will see that this property, and specifically this part of linear algebra, it helps us to work with vectors in any number of dimensions, whether it's thousands, millions, billions. This mathematical flexibility is super important for more complex data structures, for matrix multiplications, when, for instance, we are doing different algorithms, including how we can represent very large matrices, very large feature spaces. All this different information we can represent just by making use of vectors coming from this specific part of linear algebra. Let's now finish off this module by looking into some applications of vectors. So one common application of making use of vectors is when we are performing different operations while having words and we want to count those words. So this is a super common application of vectors, and we can count these words, and you can even plot a histogram of how often each of these words appear in a document. So a vector of a length n, for instance, can represent the number of times each of these words in a dictionary of n words appears in a document. So just for the sake of simplicity, let's assume that we got a dictionary that contains only 3 words. Of course, in reality, the dictionary, what we also refer often as a corpus, it contains much more many words. But for the simplicity, we will assume that we just got 3 different words in our dictionary. So that's the total. Now, let's assume that we got a document with these different words, and we want to count how many times each of those words that we got in dictionary actually appear in our document. So, if our document is described by this vector, so it contains an entry of 25, 2, and 0, it means that in our document, we got 25 word 1 from our dictionary, so in the position 1, 2 times word 2, and 0 times word 3. So basically, we have a predetermined set of words in our dictionary, in this case 3 words, word 1, word 2, and word 3, and they have a specific index, specific position in our vector. And when we are putting these values in here, then the machine or the computer, the program will understand that if we have 25 in the first position, then the word 1 in the dictionary appeared 25 times in our document, whereas the second word appeared only 2 times, and the last word, word 3, didn't appear at all, so 0 times in the entire document. So let's look into a practical example, actually, to make even more sense. So this is, by the way, a common practice to count different variations of a word. They are a common application in n-grams, large language models, transformers. They are just a cornerstone of many language models when we want to count the words in the document to understand how often the word appears, because this gives us an idea what this document is about. Knowing how many times the same word appears in that document, it gives us an indication of the topic of the document. Also, we can make use of it to do sentiment analysis to understand what this document is about, not only in terms of the topic, but also is it a positive, is it a neutral, or a negative document, so to say. So, for instance, if we got the following words that correspond to our dictionary, and in our dictionary we got just let's say 6 different words, then what we can do is that we can say 3, 2, 1, let's say 0, 4, 2, and the corresponding words are word, row, number, horse, eel, and then document. What this means is that we have a text, what we refer as a document, that contains 3 times the word word, that contains 2 times the word row, contains 1 time the word number, 0 times the word horse, and 4 times the word eel, and 2 times the word document. So this is basically a common way representing the frequency of the words in the document. Let me actually give you another example. And in here, I want to emphasize another thing, the concept of stop words. So let's say I make this 10, and then here I say there is a 3 times the word I, 2 times the word reading, 2 times the word library, 4 times the word book, 0 times the word shower, and 10 times the word So you can see that in here we are dealing with a document that contains 10 times the word which is something that we refer as a stop word. So those are things that actually don't give us too much information about what the document is about, because is just used everywhere, but it is appearing too often. So you can see 10 times, the most frequently appearing word. This is what we refer as a stop word. And then another thing that we can observe, the second thing we can observe, is that we are dealing most likely with a document that describes library, reading, because you see the words like reading, you see the word like book, library, but another word, shower, that is totally unrelated to reading, book, or library is appearing 0 times. So even by looking at these counts, we can already get an idea what the topic of this document is about. So you can see already now from this very basic example where I made too many assumptions regarding how small the dictionary should be, you can even see now how we can use these counts in our dictionary from our text in order to get idea about the topic of the document or topic of the conversation. It can be a topic of the tweets. If you have a tweet data, it can be topic regarding a book. If you have many book texts, it can be, for instance, the topic of the review. If you got product reviews from Amazon, for instance, using this count can help you to get a topic regarding topic from that text. Then you can also use it to remove the stop words, because usually the stop words are the most frequently appearing words. It can also give you an idea about the sentiment. For instance, here we are dealing with a neutral sentiment. It's not positive, it's not negative. It's just reading a book in library, that kind of topic. So all this can be super helpful when it comes to natural language preprocessing. That's a field where this text processing, text cleaning, and then using that for modeling purposes is what plays a central role. It also plays a super important role in the large language models, in the transformer models, and in the simple matters like bag of words or in the TF-IDF. All these, they are based on this idea of counting words and how we can use this information. And you can see how vectors come into play in these different applications of linear algebra in data science, natural language processing, in artificial intelligence, in machine learning. So they are super important. Another application of vectors can be representing customer purchases. For example, an n vector P, so let's say P, can record customer purchases over time, with Pi being the quantity or dollar value of an item I. Now, what does this mean? So let's say we have vector P that represents the customer's purchases, and we are dealing with a single customer, and we are just saving over time that information, how many times this customer has made purchases over time. So the quantity is in the dollars, so the dollar value of item I purchase. So we are basically keeping track of what is the value of the item I that the customer has purchased. So what we can do is we can assume that in here, actually, it already makes that assumption. It says n vector, which means that the number of rows or number of items that the customer purchases is n. Now, what the problem says that it represents is that in each entry, and here we have in total n entries, we got a dollar value of item I, which means that here if I have P1, P2, all the way to Pn, and here somewhere in the middle I got Pi in the east position, it means Pi represents the value of item I. So, for example, if I'm dealing with a customer that buys, let's say, courses, and the first item that the customer is buying is a mathematics course. So I'm writing mathematics course, and this is the first course that it buys. E is, by the way, just a way to refer to the ease purchase. So let's say here, somewhere in the middle, the customer decides to buy a deep learning course. Deep learning course. And then it continues buying, the customer continues buying courses. And the last course that the customer buys is, let's say, career coaching course. Now, let's say the mathematics course costs around $1,000. Let's say the deep learning course costs $3,000. And then let's say the career coaching service, which is usually one of the most applied and personalized one, can cost all the way to $5,000. Now, we see that in the east position, this is the east position. Let me change the color, by the way. So let's say this is the east position. This is the first position, and this is the last position. So those are just indices. We can see that in the east position, we got the 3,000, which means that the PE is equal to $3,000. So this indicates that in the east purchase, the customer purchased deep learning course, and the value of that item was equal to $3,000. All right, so now we are ready to go on to next major topic, which is about vector addition and subtraction. So we are going to do some operations and apply these operations to vectors. So let's first formally define this idea of vector addition. So two vectors of the same size are added by adding their corresponding elements. The result is a vector of the same size. So let's unpack this. It says two vectors of the same size are added by their corresponding elements. So here it refers to two different vectors, let's say vector v and vector w. And it says let's add them, what we refer as vector addition. And says for that what we need to do is to take all the elements of v and then all the elements of w, and using their corresponding elements, so indices, that helps us to understand where those elements are located, we are using in order to add each element in the vector v to the element of the vector w in the same position. And do note that in the second part, it says the result is a vector of the same size, because we are adding two different vectors of the same size. It's mentioning here. It means if we add two different vectors to the same that have the same size, we are going to end up with a vector that has the same size. Now, once I go into the examples, it will make much more sense. Let's quickly also look into this concept of subtraction. So on its own, subtraction is very similar to this idea of addition. So if we have a subtraction, let's say we have vector v, we subtract vector w, then we are doing basically what we just did to the addition, only instead of doing add, we are doing subtract. So again, we are just subtracting from vector v, vector w. They have the same size, so we end up having the result, which is a vector of the same size. Only one thing that you can see is that this can be also rewritten as v vector plus and then minus w. So we basically can represent subtraction on its own as a way of adding, only we take the negative, so the opposite directed vector. So this will make even much more sense once we go on to the examples. So let's look into our first operation example where we are adding two different vectors. This is a basic example. We got just two-dimensional two vectors. We got vector A that has entries 2, 3 and vector B that has entries 1, 4. And what we are doing is that we are adding vector A to vector B. We just learned that A, we need to have the same size of vectors. So you can see that vector A has a dimension 2 by 1. Vector B has a dimension of 2 by 1. So their sizes is the same. Both they got two entries only, two elements. And at the same time, we just learned that what we need to do is to take their corresponding elements and add them to each other. Now, what does this mean? It means that we take from A the first element 2, and then we take the first element of the second vector, which is the B. So we take the 2 from here and 1 from here, the first element of A and the first element of B, and then we are adding them to each other. 2 plus 1 is equal to 3, and then the same holds for the second entry. So 3, which is the second element of vector A, and then 4, which is the second element of vector B, we are saying 3 plus 4 is equal to 7. So let me write it down even in a simpler manner such that it will make much more sense. So vector A has elements 2, 3. In the first element, we got 2. In the second element, we got 3. So A. Then we want to add B, which has in the first element equal to 1, and the second element is equal to 4. This means that if we want to add these vectors, 2, 3 plus 1, 4, this is equal to, we need to take 2, we need to add 1, so this element and this element, and then we need to take 3, we need to add to 4, so this one and this one, which is equal to 2 plus 1 is equal to 3, 3 plus 4 is equal to 7, so we got vector 3, 7. Do note that this vector, the result vector, contains again two elements and just one column, so 2 by 1. So you notice that the size is the same of this result vector. Now let's actually generalize this concept before moving on to the next example. So if we got, let's say, vector A that contains n elements, A1, A2, all the way down to AN, and it is from n-dimensional space, and we got vector B that also has n elements, so remember that they both need to have the same size, so B1, B2, all the way to Bn. So they come also, so B comes also from n-dimensional space. So then when we add A to B, this is equal to A1, A2, all the way to AN plus B1, B2, all the way to Bn. So n by 1, the sizes, this is equal to, let me actually use this color to make it even more visible. So for the first entry, for my result vector, I will get A1 plus B1, then A2 plus B2, So all the way down onto the nth element, which is an plus, let me use a different color, a1, b1, b2, bn. So you can notice now, in general terms, what we are doing here. So we are taking the a1 coming from the vector a, we are adding in the same position the value that comes from vector b, which is b1. We are saying take the a1 plus b1. This is the first element, so the position stays the same, and then in the result vector. So we take all the corresponding values that have the same position in the corresponding vector, first from vector a and then vector b. We are adding them, and this forms our new vector. And this new vector will again have a size n by 1. So you can see that the sizes of the two vectors are the same. Both have n elements, and then we are using their corresponding elements to add them to each other element-wise. And then we are getting the result that has the same size, so n by 1. So this is a more general description of how you can add two vectors. Let's now look into the specific example. So we have a vector with the entry 0, 7, 3. So this comes from R3, you can see, so three-dimensional vectors. The second vector is 1, 2, 0. And then the final result is 1, 9, 3. So how we got this? We took 0, we added 1, 7, we added 2, and then 3, we added 0. So you can see all these elements, element-wise. And then this is equal to 0 plus 1 is 1, 7 plus 2 is 9, and then 3 plus 0 is 3. Exactly what we got here. So again, the same sizes, and the result is from the same size. So quite straightforward. Now when it comes to the vector subtraction, what are we doing that? So what are we doing here? So we are doing kind of very similar thing. We are taking this element 1, we are subtracting the other one in this first element. Then we are taking the 9 in the second position and subtracting this again from the second position of the second vector. And we are putting in here 1, and then 1 minus 1 is equal to 0, 9 minus 1 is equal to 8. So we get a result vector 0, 8 like in here, and you can see that the sizes stay the same. So also in this case, let's write more general this idea of subtraction. If we got a vector a from Rn, so n-dimensional space, and it can be represented by a1, a2, all the way down to an, so it has n elements, n by 1. And then we got b also from Rn, so coming from the n-dimensional space, which means that it got n elements, so b1, b2, all the way down to bn, again with the same size, n by 1. Then a minus b is simply equal to a1. Let me actually use the same colors to make it easier to follow. So let me first draw my square races, and then here I will use blue for A and then red for the color for second vector, which is B. Here I will use black minus then, given that the same size should be for the result vector, I already know that I expect n different elements for this. And then here, I'm taking this first element that comes from vector A. I'm subtracting from this the first element that comes from vector B, so element-wise subtraction, B1, and I'm already getting the result for the first element in my result vector. So you can see A1 minus B1. I'm taking this element and subtracting them from each other to get A1 minus B1. And then the same holds for all the other values, only coming from different elements from vector A, subtracting from this the corresponding values element-wise from the vector B, so B2, B3, all the way to AN. So you can see that in my result vector, A vector minus B vector, in the first element I get A1 minus B1, then A2 minus B2, then A3 minus B3 in the third element, all the way down to the nth element, which is equal to, this should be B, AN minus BN. So this already should make much more sense. So every time we take the element in the same position from one vector than the other, we subtract from each other in order to get the corresponding element in the final vector. All right. So let's now, before moving on to the properties, I want to show you this only in a coordinate space. So what this means in terms of visualization in a coordinate space. So let's say we have a coordinate space This is my y-axis. This is my x-axis. So this is x and the y, and this is my center. So 0, 0. And what I'm doing here is simply I want to have vector A. Let's say this is just vector, a simple one with the coordinates, let's say 4 and -2. And I got vector B. Let me use a different color. Vector B that has coordinates, let's say -4 and 4. So let's actually visualize them. Let's first start with the vector A, which has a x value of 4, 3 and 4, 1, 2, 3 and 4, and the y value -2. So this is my vector A. And let's now visualize the vector B. So -4 and 4, which means that, let me actually extend this. This is -4, so the x coordinate is -4. So it should be here. And then the y coordinate is 4. So 1, 2, 3, and 4. It's this one, which means that my vector B is this one. All right. So you can see now that the vector A is in here and the vector B is in here. Now, what I want to do is to add these two vectors to each other. So what I want to do is to take this vector A and add to this the vector B, which is equal to 4 minus 4, it was 0, and then -2 plus 4 is equal to 2. So 0 and then 2, it is 0 and 2. So this is my result vector. So now when we are clear on how we can add vectors, how we can perform these different operations, and what it means in practice when it comes to looking at the vectors in a coordinate space and adding them or subtracting them, we are ready to look into the properties of vector additions. So this is something that will definitely seem familiar to you from pre-algebra, where we are basically using all these properties that we already know that holds for numeric values, for the scalars, that being transferred to this vector space. So we are going to talk about these 4 different properties that the vectors have. The first one is the cumulative property, which says that if we add a vector A to vector B, then this is the same as adding a vector B to vector A. So basically, the order of the vectors doesn't really matter when it comes down to adding them. So formally, A plus B is equal to B plus A for any vectors A and B of the same size. Then we have associative property, which says A plus B plus C is equal to A plus B plus C. We can write both as A plus B plus C. Now, what does this mean? We know from pre-algebra that this parenthesis means first do this addition and then do the rest of operations. In here, it basically says if you add A to the B first and then you add the C, is the same as first you add B to the C and then on the top of that you add the vector A. So then the third property is addition of 0 vectors, which says if we add a 0 vector to vector A, then this is equal to adding a vector 0 to A, and this is equal to vector A. So adding the 0 vector has basically no impact on the vector whatsoever. Then the final property is subtracting a vector from itself, which means if we take the vector, we subtract the same vector from itself, so A minus A, and we get a 0 vector. So A minus A is equal to 0 vector, and this yields the 0 vector. Now let's look into each of those properties one by one, and let's look into specific examples. In some cases, we will prove this on the example that we have to make this concept much more clear. So let's start with this cumulative property of vector additions. So we want to see whether A plus B is equal to B plus A. So let's say we have a vector A that has coordinates or magnitude and direction that is equal to 1 and 2. Then we have a vector, let's say B, that has a magnitude and direction of -2 and 3. So the first thing that we want to check is indeed whether the A plus B is equal to B plus A. So therefore, let's first calculate this part, and then we will calculate this part that I will define by 1 and 2, and we will see whether we are indeed having the same value, the same vector or not. So let's see. So we have here A. So A plus B, which is the first value that we want to calculate. A plus B is equal to 1, 2 plus -2, 3. And we learned before that this is simply equal to take this value and then add this one. So 1 plus -2 and then 2 plus 3. So this gives us a vector 1 minus 2 is equal to -1 and 2 plus 3 is equal to 5. So we get that A plus B is equal to -1, 5, this vector. Now let's look at the second quantity. So B, vector B plus vector A. This is equal to -2, 3 plus 1, 2, and this is equal to -2 plus 1 and then 3 plus 2. This gives us -2 plus 1 is equal to -1 and 3 plus 2 is equal to 5. So we can already see from here that the quantity 1 is indeed equal to quantity 2, which proves that indeed the A plus B is equal to B plus A. What this basically means is that adding two different vectors, the direction or the order is not important. Whether you add A on the top of the B or B to A, it doesn't matter. At the end, is the same. And actually, you can also see it if you combine this or if you do this in more general terms. So let's say if we have a vector A, which is equal to, in an n-dimensional space, A1, A2, up to AN, so it has n by 1 dimension, and you have a vector B with the same size from the same Rn dimension, and it has elements B1, B2, up to Bn, and the dimension is equal to n by 1, then if we calculate first A plus B, and this is equal to simply A1 plus B1, A2 plus B2, up to AN plus Bn. And if you calculate the second amount, which is B plus A, and this is equal to B1 plus A1, B2 plus A2, up to Bn plus An, you can see that A1 plus B1 is equal to B1 plus A1. Simply from pre-algebra, you know that if those are all constants, for instance, 2 plus 3 is equal to 3 plus 2. In the same way, A2 plus B2 is equal to B2 plus A2, and then here up to AN plus BN is equal to BN plus AN. What this means is that all these elements, they are basically the same, which means that we already have a proof, so we get this proof, and we can see that even for the general term, independent what this vector A is, what this vector B is, that A plus B is equal to B plus A. This is exactly what we saw before in the first property, which is called commutative property of the vectors, that the A plus B is equal to B plus A. Now let's move on to the other property, which is called associative property of the vectors. Now, what this property does and says is that A plus B, so first we do this, plus C is equal to A plus B plus C. And this is then equal to A plus B plus C. Now, let's then see this specific property on an actual example. So what this basically says is that if we have this example where A is equal to, actually, I had this before. Let me simply just remove this part. Let's then add our third vector, which is C, and let's call it, let's say, it has a representation of 4 and 5. Then the idea behind this property is that what we need to prove here, that A plus B within the parentheses plus C is equal to A plus B plus C, and then this is equal to A plus B plus C. So let's see actually whether this is indeed true for this specific case. Now, this should come very intuitive, so I'm going to do it very quickly. So first we have this quantity, this one, then we have this one and the third one. Let's do it very quickly. So A plus B plus C is equal to 1, 2 plus, and then we add C, so it is simply 4, 5, and then this is equal to, we saw before when doing this, that we were getting 1 minus 2, 2 plus 3, and then we add this 4, 5. This is simply equal to 1 minus 2 is minus 1, and 2 plus 3 is 5, plus 4, 5. Now, given that it doesn't really matter no longer that we have here parentheses or not, this basically means that this value is simply equal to minus 1 plus 4. So here minus 1 plus 4. Here 5 plus 5. So this is then equal to 3 and then 10. All right. Let's then now quickly do the second amount, which says first add the vector b to vector c, and only then add the vector a on the top. What this means is that we need to take 1, 2, this is vector a, and we will only add this once we have added the minus 2, 3, the vector b, plus to the vector 4, 5. Okay, so we can see that we are just leaving this in here. Let's first add this 2. Minus 2 plus 4, 3 plus 5. So this gives us 1, 2 plus minus 2 plus 4 is 2, and then 3 plus 5 is 8. So this gives us, let me remove this calculations. So this gives us 1 plus 2 is equal to 3, and then 2 plus 8 is equal to 10. Okay, great. So now we got already the quantity 1 being equal to quantity 2. Let's check whether this is all equal to this one. It should already be something that you see now, given that we know just from mathematics that parentheses doesn't really matter when it comes to the scalars, and adding two vectors is basically very close to this idea of additive property of the scalars. But just let's quickly do it to be 100% sure. So when we take this vector a to the b and to the c, we add all this. This is equal to 1, 2, added 2, minus 2, 3, and then added this to 4 and 5. Now, what this is equal to, let me actually write this in a bit shorter way such that it can be all fit in this small place. So 1, 2 plus minus 2, 3 plus 4, 5. This is equal to basically 1 minus 2 plus 4, and then 2 plus 3 plus 5. And what is this number? One minus 2 plus 4 is simply equal to 1 minus 2 is equal to minus 1, and then plus 4 is equal to 3. So first element is 3. 2 plus 3 plus 5 is equal to 5 plus 5, which is equal to 10. Perfect. So now we get the confirmation that indeed a plus b plus c is equal to a plus b plus c is equal to a plus b plus c. So let's quickly also look into this addition of zero vector and the subtracting a vector from itself properties, and the detailed explanation of this or example of this I will leave it to you. So when it comes to this a plus 0 is equal to 0 plus a is equal to a, so this property, let's say if a is equal to this 2, 3, and then we are adding on this a plus some 0 vector, which basically means take 2, 3, and then added the same size of 0 vector, you can see that this is the same as adding just zeros on these values. Now, what do we get? We get that this is equal to 2 plus 0 is 2, and then 3 plus 0 is 3. There we go. So we already see very quickly that it doesn't really matter whether we add a 0 vector to this original a vector or not. In all cases, it just adding a 0 vector has no effect. And seeing from the cumulative property that a plus b is equal to b plus a, we already know that if a plus 0 is equal to a and is equal to this, then also 0 plus a will be the same. And we can see indeed that we just saw that a plus 0 is simply equal to a. So we basically have quickly proven all this. Now, when it comes to the subtracting a vector from itself, I think this is a very nice one just to see how we take the same vector and subtract from that value and we get 0. And this is very similar to working with just real numbers. In the same way as 3 minus 3 is equal to 0, also when we have a vector consisting of the scalars, like a is equal to 2, 3, in the same manner, if we take this a and we subtract it from itself, so a minus a, then what we will get is 2, 3 minus 2, 3, and this will give us 2 minus 2 is 0, and then 3 minus 3 is 0. So we get a vector 0, so 0 vector. So now when we are clear on how we can perform different operations on our vectors, and also we know what are the properties of adding and subtracting different vectors, we are ready to move on to a bit more advanced topics. So in this module, we are going to discuss this idea of scalar multiplication. We're going to look into the example, what happens and how we can do the vector multiplication with the scalar. Then we are going to look into the span of vectors, what it means to have a span of vectors, what is this idea of linear combination and the relationship between the span and linear combination and the unit vectors. Then we are going to look into the application of scalar vector multiplication in audio scaling example. And then finally, we are going to finish off this module by looking into the length of a vector and a dot product. And we are going to go back to this idea of distance, understanding vector magnitude, and understanding vector length. So let's get started. Now, before we look into this idea of span and linear combination, I quickly wanted to look into this idea of scalar multiplication and the specific definition of it. So formally, the scalar multiplication involves multiplying each component of a vector by a scalar value, effectively scaling the vector's magnitude. So what do I mean here? Let's say we have a vector, and I will write it in the general terms to keep everything general. So let's say we have a vector A. Let me pick up my pen. A. And this vector A is from n-dimensional space. So it is from Rn, and it can be represented by A1, A2, up to An. And I have this magnitude of a vector. And now I want to scale this vector for which I know the magnitude and the direction. I want to scale it with a scalar. And we learned before that the scalar is just a number. So scalar, in this case, I will be referring it to by C. So C will be my scalar, and this comes from R, which means that it's a real number. Let me actually use a different color to make it easier to follow. Okay, so my scalar will be with the color red. So C, and C comes from R. So what do I mean by scalar multiplication? I mean that I want to find what is this C times A. This is what we mean by scalar multiplying with a vector. Now, what does this definition say? It says when we are multiplying scalar with vector, so the scalar multiplication, meaning multiplying vector with the scalar, it involves multiplying each component of a vector by a scalar value. So if we translate it to this specific example, it means that this amount, so this amount is equal to taking C and multiplying it with each element of this vector. So each component of a vector. And what are the components of my vector? The A1, A2, A up to the point of An. So all these components. So that means that the first element of this new vector, the scalar multiplication result, will be C times A1, C times A2, ... So all these middle elements, and at the end, again, C times, and then An. And then in both cases, of course, the number of elements doesn't change, so the number of rows of my vector doesn't change, it's n. So here also n. And then number of columns is the same, so it's just a column vector, so one column. So what we see here is that we go from A1 to C times A1, we go from A2 to C times A2, up to the An transforms into C times an. So we see very easily that I keep all the elements from this vector, I take them in here, and instead what I'm doing is that I'm multiplying every element from this vector by the scalar c. So this is exactly what this definition says. And let's actually go ahead and do a hands-on example with some real numbers to have this method and to have this definition very clear in our mind, because we are going to make use of this fundamental operation, scalar multiplication, on and on in the upcoming lectures and just in general in your journey in any applied sciences. So this is an example of scalar multiplication. Here what we are doing is that we want to multiply this vector c. So in this case, the vector is defined by a letter c, and then on the top we can see the arrow indicating that this is the vector now. And here we refer the scalar by a letter k. We are saying we want to perform scalar multiplication, which means that we want to multiply the vector c by the scalar k. So how we can do that? So what we want is to multiply k by c, and we just learned that for that, what we need to do, let me write this over. So this is equal to minus 2 multiplied by 4 minus 3. This is my vector. So this is the k and this is the c. This is equal to, so I take my scalar and I multiply it with each of the element of the c. So minus 2 times 4 and then minus 2 times minus 3. So minus 2 times 4 is equal to minus 8, and then minus 2 times minus 3, so minus minus, it goes away, it becomes a plus, and the 2 times 3 is 6. So my end result, the k times c, is equal to minus 8 sixths. This is my final result. So let's quickly also do yet another example. And this one is a unique one because it's relating to this idea of multiplying something with a 0, which is something that we also know from a high school, that when we multiply a number, let's say 7 by 0, we are getting 0. And here, in this example, the problem is describe the effect of a scalar multiplication by 0 on any vector, which means what we are doing is that in this example is we want to know what is this result of any vector, let's say vector c. So we will use the same example, c. Only this time, instead of multiplying it with the scalar k equal to minus 2, our scalar will be 0, which means that c is equal to 4 minus 3, and then the k is now equal to 0. And we want to find out what is this k times c. Let me actually write down the k with a different color. Good. K is equal to 0. So what we want to find out is k times and then c. And this is then equal to 0. So I'm taking the k 0 times, then I'm taking each of the elements of c, which is 4 and then minus 3. And I know that when multiplying the number with a 0, it gives me 0, which means that I end up with 0 here. 0 times 4 is 0. 0 times minus 3 is also 0. So I end up with a 0 vector. Now, this gives me an idea already that I can make a general conclusion that independent of the type of vector that I have, independent what are these values in my c, if I have any vector c and I'm multiplying it with 0, then this will always give me a vector of 0, because all the members of this final vector will be just zeros. So if, for instance, the c comes from let's say Rn, so it has n different elements, it comes from n-dimensional space, then my final result of 0 times c, so this 0 vector, this one, so 0, this one will come also from Rn. So you will be having a vector, so 0 times c will then be equal to 0, 0, blah, 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 0. So n times zeros. So this is then the idea of multiplying, so scaling a vector with 0. And this is our example 2. All right. So let's now move on to our application of scalar vector multiplication. And then after this, we will go back to this idea of linear combinations and the spans. So in this specific application, we have a scalar vector multiplication, and we are looking into application of audio scaling. So the scalar vector multiplication audio processing, this can change the volume, for instance, of an audio signal without altering its content. So you might have noticed that when you are listening to a video, you can simply increase the volume of that video or decrease it. But you will notice that the content doesn't change. You are just increasing the volume or decreasing it. Even on the TV, when you are watching a show, you are increasing the voice or decreasing. Now, what you're basically doing behind, and this is super interesting, is that behind the scenes, what is happening is that there is simply audio that contains that show, and the audio of that show is being multiplied with a scalar. And that scale is simply the volume scale. If you scale it in such a way that you want to decrease the volume, so the audio will then have a lower volume, then you are simply multiplying it, your vector containing the audio information in such a way that those newer volume indications, they will be containing lower numbers. Hope this makes sense. Let's look into the example. This will definitely clear this out. So let's assume we have a vector A that represents the audio signal. And we want to multiply vector A by a scalar B to adjust the volume. So B is some sort of number. It can be, so B comes from R, so it is a real number, while A is simply a vector. Given that it doesn't mention it here, I'm assuming that A comes from Rn. So it comes from n-dimensional space. So imagine of A as this vector, A1, A2, blah, 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 up to AN. And each of these values, it basically describes the audio signal. So it represents an amount, so it contains an amount that represents the audio signal of your video or your show. And then the B, in this case, for instance, in this example, you can see that the B is then equal to, for instance, 1 divided to 2, or B is equal to minus 1 divided to 2. So you can see that B is equal to 1 divided to 2, which basically is a fancy way of saying that B is equal to 0.5, or B can be equal to minus 1 divided to 2, which is minus 0.5. Now, then it says, then the B times A, which basically means multiplying our scalar beta by the vector containing the audio signal A. So this B times A is perceived as the same audio signal, but at the lower volume. Now, why lower? Because you can see that B is equal to 0.5 or minus 0.5. It means that once you take all these elements of your A and you multiply it with a number that is smaller than 1, in this case 0.5, then all these numbers will decrease, which means that also your audio volume will decrease. So let me actually show you an example. So let's say our talk show is very short and the audio variation is very low. You have a vector A that is quite small. It comes from a three-dimensional space, so R3, and it has numbers like 3, 6, and then 5. So 3 by 1 vector. And then we have our audio adjustment scalar, beta, which is equal to 0.5. Now, when we take the beta, we multiply it by our audio signal. Then what we do times, make this clear, so times, what we are doing is that we are simply taking all the elements of our A, so 3, 6, and 5, and what we are doing is that we are multiplying it by 0.5, 0.5, and 0.5, or you can also say 1 divided to 2. So what this is equal is that 3 times 0.5 is 1.5, 6 times 0.5 is 3, and then 5 times 0.5 is 2.5. And you can see that all these numbers, 1.5, 3, and 2.5, they are smaller and specifically 2 times less than all the original values in the original audio. So original audio is A, which was 3, 6, and 5. And the new audio, the scaled one, is, so audio scaled, so B times A is equal to 1.5, 3, and 2.5. So you can clearly see this transformation where this element 3 is larger than 1.5, 6 is larger than 3, and then the last element 5 is larger than 2.5, which means that this audio is much at a higher volume. So the volume 2 times higher than this audio. So this is basically the idea of applying scalar multiplication to our audio preprocessing. I will leave the other example to you that will show that when your scalar is equal to minus 0.5, you again will end up with a lower volume. Only that time, the volume will be much, much lower than the original one. So now that we know how we can perform scalar multiplication in theory, as well as we have looked into an example, how we can do it in terms of the numbers and multiplying them. And we have also seen applying scalar multiplication in practice. So we have seen in this audio processing stage, the multiplication process. We are ready to look into the visualization of it. This will help us to get a better understanding on what exactly happens when we are scaling different vectors. Let's look actually in the following example. So let's assume we have a vector. Oh, let me remove that. So let's assume we have a vector, and that vector is, let me get a color, this one for instance, a vector A. And this vector A consists of elements 1 and 2. So where does this vector lie? The vector is with 1. So here in our coordinate system, this is our x-axis, this is our y-axis. And here we got, let me actually pick another color. Let's say black 1. And then we got 1 and then 2. Right? This is 2, this is 1, so it is this one. So the line that we get here, it is this one. So this is our vector A. Now let's assume I want to multiply my vector A. So I want to scale my vector A by a constant tree, by a scalar tree. So I have a scalar, let's say I call it K, and this K is a different number. Let's say K is equal to 3. So what I wanted to do is to perform a scalar multiplication. So I want to obtain K multiplied by A. And we learned that this is simply equal to 3 times, and then 1, 2, and then this is equal to 3 times 1, 3 times 2, which is equal to 3 and then 6. So let's also visualize this scaled vector. So let me pick this yellow color. This will be our scaled vector. So we have done scalar multiplication and we are going to visualize that. So we have 3 and 6. So this is 3, 1, 2, 3, and this is 6. So we have this point. So you should already see what is going on here. So we got 3a here. So you can see that this part is our vector a, and this longer one is 3a. And even visually, you can see that this longer vector is simply the 3 times of the shorter vector. So we got this, and then if you add on the top of this the same 3 times, you will then end up with the original, so scaled version of that. So basically, this is A, this is A, this is A. We combine 3 different, so we scale A 3 times, and we simply get a 3 times longer version with the same direction. So you can see that when we are scaling, even visually, it makes sense. So we are scaling our vector A 3 times, and we are just getting that vector. So we are transforming. Well, let me remove this. So basically, we are taking this vector and we are scaling it up to this point. If I would do it only 2 times, then it would be something like this. Or 1.5 times, it would be something like this. So only half of it. So now this should make much more sense. Let us actually do yet another example to make sure that we are clear on these visualizations, because we are going to make use of it when looking into this idea of linear combination in a span. So let's say we have a vector B, and this vector B has elements 0 and 3. So let's visualize and plot this vector. So it contains elements 0 and 3. So 0 and 3. So this is the x element and the y element. On the y-axis, we can see this is 3, which means that our vector B is this vector. All right, perfect. So this is our B. Let's now multiply, so scale our vector B by a scalar 2. So let's say we want to get 2 times B. So what is this amount? This is equal to 2 times, and I'm simply taking each of those elements, 0 and then 3. So this is then equal to 2 times 0 is 0, and then 2 times 3 is equal to 6. So this is my new scaled vector, 2 times B vector, this one. So let's visualize this. The x-axis value is 0, so we are still here. And then the y-axis value is 6. So what is 6? This thing. All right. So you already should see that this is very similar what we had before. So this is 2b. All right. So this all should make sense. Also, we learned as part of the high school when visualizing different plots. So this is quite similar to this idea of having y is equal to x and then scaling it, getting like y is equal to 2x. So in this case, only we know exactly where the vector starts and ends. So we have a much more specific definition instead of having all this infinite number of points on the line. But the idea stays the same. So we are taking this vector and we are then scaling it 2 times, so we get 2b vector. And I could do the same, only instead what I could also do is I could do like 0.5 or 1 divided to 2 times b. So I take the half of it, which means I would get this vector. Or I could multiply it with -1, so minus 1 times b. So I would scale with -1. And then I would simply get the negative version of my original vector. So this thing. This would be minus b, or minus 1 times b. So this is basically the idea of scalar multiplication when visualizing it in our coordinate system, Cartesian coordinate system. And now when we know all this, we are ready to move on this idea of linear combination. So let's now talk about another super important topic, which is the dot product and its applications. So we are going to talk about the dot product, and we are going to make this relation between the dot product and the distance, something that we have learned as part of the high school. So the dot product, we are going to understand it, we are going to plot it, the vectors, we are going to perform this dot product in examples, as well as we are going to look into the properties of the dot product and the inner product concept. We are going to see the relationship between dot product and inner product. We are going to talk about the Cauchy-Schwarz inequality and the geometric interpretation of it. So those are really important concepts, the Cauchy-Schwarz inequality, the intuition of it, as well as the implication of it, specifically in machine learning. And then we are going to talk about the vector triangle inequality, and in what cases also the norm is equal to 0. And finally, we are going to define the angle between vectors. So when it comes to the dot product is also known as the scalar product. It's a fundamental operation in linear algebra. It combines the two vectors to produce a scalar. It's a way to measure how much one vector extends in the direction of the another one. So providing insights into the geometric and the algebraic properties of the vectors. So when we are using this operation of the dot product, you can see it as an operation that we apply to vectors. And in this way, once we look into the geometric side of it, so we will visualize the vectors and we will see the geometric insights behind it, it will all make much more sense, because this will relate back to our geometric interpretation, this idea of Pythagorean theorem, because they are highly related, this idea of distance, and how by using the dot product, we can relate all these different concepts. So let's first formally define the idea of dot product. So the dot product of a vector v with itself gives the square of the length of v. So earlier, when we were looking into the prerequisites of the course, I did briefly mention that we need to know this ideal length of a vector or length of a line. We said that we denoted this by this concept or by this notation of two straight lines and then the name of the vector and then another two straight lines, and this is what we refer as the length of a vector. So the distance between 2 points, so the starting point and the end point where our vector is described. So if we have, for instance, this vector, then if we take this point and we take this point, then we can use that in order to calculate the distance of this vector. And the distance of this vector is defined by this notation. So that's exactly what we have here too. So you can see that we are saying that the dot product is actually this v. So we take the vector, we multiply with itself. We are saying this is the dot product of a vector, and it is equal to the square of the distance or the length of the vector. So in the left-hand side, we have this notation of the dot product. We just use this dot as usual with any multiplication or any products. And we are saying this is equal to, and we take the length of a vector v and we square it, and this gives us our dot product. Very soon we will see, when applying it on more general terms, what this idea of dot product is when we apply it to vectors just in general. So in a two-dimensional space, when we have each vector represented by two numbers, let's say vector v, which is equal to x and y, so we have on the first element the x coordinate of our vector in our Cartesian coordinate system, and the second element, so this one, is the y, so from y-axis on our Cartesian coordinate system, then the dot product and the length are highly related as usual. So we have here v, the vector, and then again, so dot product of vector v is equal to x squared plus y squared. So this is the length of this vector, and it is equal to then the square of this length. So let's actually plot this to see it in our coordinate system such that we can relate this back to the Pythagorean theorem, and we can see how it is possible that the dot product, the v times v, which is equal to the square root of the distance, is actually equal to x squared plus y squared. So let's assume we have this vector v, and this vector v is represented by this x and the y. So we are in the R2. So this is our x-axis, this is our y-axis, and in here, our vector v can be represented, and I'm just taking some random point, and I'm saying this is my x, and this is my y. Then this is simply the vector v. So this x and y, this can be random numbers. I just want to keep it general and to make it very similar to the definition what we just saw. So we are going to relate this back to the Pythagorean theorem, and we are going to prove how Pythagorean theorem is related to this vector, and that the dot product of this vector, so v times v, is actually equal to the square root of the distance of this vector v, and then on its own, this is then equal to x squared plus y squared. Alright, so the first thing that we can do is to check and use the Pythagorean theorem in order to prove that the length of this vector, and so the distance from this point to this point, is actually equal to x squared plus y squared. And to be more specific, square root of x squared plus y squared. So when we look in here, one thing that we can see is that this side, which is the side that we can have here in order to form our triangle. So I want to take the beginning where my vector starts, and I want to see what is that we have in here. So this side, given that this is 0 and this is x, this means that this entire distance is just x. And of course, the other way around holds as well. When we look at the horizontal side, this length, so this is the y coordinate of this point, which is y. So we see here that it is equal to this part. So we see that we are dealing with a triangle where, so this is our vector v, and we can see that this side is x, and then this side is y. Now, we also know that this angle is 90 degrees. Using the Pythagorean theorem, which states that in this type of triangles, when it is a right triangle, and we have x and y as the sides, we can compute the opposite side. So the distance or the length of this side, which is, let's call it, so in this case we have already the vector, so we can say that the length of this vector, this is how we were defining the length of the vector. This is then the square of it, according to the Pythagorean theorem, is equal to x squared plus y squared. Because the Pythagorean theorem says, if this is the 90-degree angle, here we have A, here we have B, then this side, which is defined by C, so C squared is equal to A squared plus B squared. And here the C is basically our vector, and we are saying the length of this vector, so the length of this vector is basically equal to C. from here to make it easier to compare the two. So this means that using the Pythagorean theorem, we can already find that the length of this vector is equal to the square root of the x squared plus y squared, knowing that the vector has those coordinates x and the y. Okay, so now when we are clear on what the norm is, let's actually look into what we have here. We are saying that the dot product V is equal to the square of the length of it. Now we just saw that the length of the V vector is equal to the square root of x squared plus y squared. This means that this amount, if we remove this, what we wanted to prove, so this is equal to square root x squared plus y squared and the square of it. So we just want to prove by making use of all the geometric interpretation and the phenomenon that we already know, including the Pythagorean theorem. So this is then equal to square root with the square here. It cancels out, so this two, and we simply end up with x squared plus y squared. So we already proved that the dot product that we define like this, and we are saying according to the definition of the dot product, V dot product of the V, so the vector V, is equal to the square of the distance or the length of the vector, that this, in this specific case, if we are in the two-dimensional space and our vector is defined by this x and the y, then this dot product is simply equal to the x squared plus y squared. That's something that we just proved. All right, so let's now apply it to an actual example. So here we are seeing that the length of a vector is deeply related to dot products. That's something that we just saw also when plotting it in our Cartesian coordinate system. So let's now look into this specific example. So V is equal to 3, 4. So this is the x-axis, this is the y-axis. And here the proof is that the dot product VV is equal to 3 squared plus 4 squared is equal to 9 plus 16 is equal to 25, which means that the length is equal to square root of this dot product and it's equal to 5. Now let's actually prove this just to ensure that we are at the same page. So we can actually go ahead and plot that in here. So we have that the vector V is equal to 3 and 4. So a few things just to get straight before plotting this. So we know that the dot product can be defined like this, and we said that this is equal to the square of the length of this vector. And we also proved that this is also equal to the x squared plus y squared if we are in the two-dimensional Cartesian coordinate system. So here, this is our x and this is our y. So our x is equal to 3 and our y is equal to 4. Let's actually solve this problem and find it also geometrically to prove what is the dot product and what is the length of this vector. So the vector V is 3, 4, which means that it is 1, 2, 3. So this is 3 and this is 4. So we are here. And this is our vector V. So this also means that one of the sides of our triangle with 90 degrees angle, so our x, so this is our x, and then x is equal to 3. So x is equal to 3. And our y is equal to 4. So it is this one. This is our y. So now we want to find what is this length. So we want to find what is the length of this vector v. So the length of vector v is then equal square root of, so it is equal to x squared plus y squared according to Pythagorean theorem. And then this is equal to, just filling in the numbers, four squared is 16. And then this is 9 plus 16 is simply equal to 25. So this is equal to 5. So in this way, we can see that we are proving that the length of this vector v is equal to 5 if the sides are 3 and 4, which means that the vector has this coordinates 3, 4. And at the same time, so in this way, we already see a few things. So we see that the length of the vector v is equal to 5. That's something that we already proved. And we also saw that the dot product is equal to the square of the length, which means that it's equal to 5 squared, which means that it's equal to 25. So, and that's exactly what we see here. It says that the dot product of v is equal to 25, and the length of that vector is equal to 5. So the dot product of the two n vectors a and b is defined as the ATB, which is equal to a1 b1 plus a2 b2 up to a n bn. So this is basically the generalization of the definition that we just saw before. So we go from the description of working with the vector v and the distance to the more general one when we are now dealing with n-dimensional vectors. So now we are no longer in a basic two-dimensional space, but we are in an n-dimensional space. And we have these two different vectors, a and b. Think of a as this vector a1, a2 up to an. And then think of this vector b as b is equal to b1, b2 up to bn. And the dot product of these two, we are writing as a, and then this small letter t, which means transpose. And we will see something very soon. We will also be discussing the topic of transpose later in the next module 2, multiplied by b. So this ATB, or A transpose B, is a bit more advanced way of writing down this idea of dot product. And the dot product of these two n vectors, a and b, is defined as this formula. So we are basically cross multiplying the two. We are taking this element from a and we are multiplying it with this one. Then we are taking this element of a and multiplying with this element of b. So we are basically taking all the corresponding elements from these two different vectors and we are multiplying them together and creating this combination and adding them up to create this single value, to represent these two vectors with a single value, which we call dot product. So this notation ATB, which is a common way of noting and denoting this dot product. This is just one way of describing this dot product. There are also people who will write down this. So you see that this triangle type of braces and then the first vector and then the second one and then this one. So you will notice one thing that will be quite different in here versus in this definition. Because in here, we were discussing the dot product of a vector. So we were talking about exactly the same vector. So here we have v and v. And we were just saying, let's take the dot product of a vector with itself. And this was related to this idea of length. When we go from one vector to this idea of multiple vectors, so now we are creating no longer the dot product of single vector, but we are defining the dot product of two vectors, A and B. The definition changes, as you will notice, but that's important to differentiate the two and to understand that one is actually not the other one, and to be able to see the difference between the two and not to confuse them. So in the upcoming presentations, we will use this notation of ATB much more often than this second notation. But if you see this, you can just know that we are talking about the same thing, which is that the dot product. So when the n is equal to 1, then this inner product or the dot product simplifies to the multiplication of just two numbers, because we no longer have vectors, but we just got a single value for A and a single value of B. So let's assume that the n is equal to 1, and then A is equal to 2, and then B is equal to 3. And then the dot product is simply the ATB, which is equal to 2 times 3, which is just 6. So when it comes to this idea of transpose, I will explain this in a bit, and we are going to describe this in detail as part of the next unit, so I won't go too much into it, but it's always a great idea to know, also for this module, at high level, this idea of transpose. This T is basically referring to this, so transpose. So to understand this idea of dot product, the dot product is an operation that takes these two vectors, vectors A and vectors B, and returns a single number, a scalar. And the single number is computed by calculating the sum of all these individual values. So it takes all these elements from one vector, then the other one, so A1 and B1, A2, B2, A and Bn, takes the value from one vector with the corresponding one from the other vector, multiplies them to each other, and then add them all up, and then this single value is created, which we refer as a dot product. So geometrically, it represents this product of the vectors' magnitudes and this cosine of the angle between them. So we already know from high school and also from trigonometry and geometry this idea of angles and what is the cosine of an angle. So I won't go too much into the detail of it. I will assume that you know what a cosine is. So the dot product is used to determine the angle between the two vectors and also to check whether they are orthogonal or not. Because we have a property that relates the dot product directly to the orthogonality of the two vectors. And knowing how to calculate the dot product of the two vectors will help us to check whether the two vectors are orthogonal or not. And just in general, understanding this concept of dot product is super important because we use dot product in machine learning, we use dot product in general in AI. You will see dot product appearing also when we are talking about attention mechanisms, so calculating this attention scores as part of multi-head attention transformers. We also use this idea of dot product, scale dot product. So it's really fundamental and essential to understand this concept of dot product for matrix multiplication, but also in general to apply linear algebra in different science-related domains. So let's now look into a specific example to understand this concept. The dot product of these two vectors, in this case we have three-dimensional vectors, A and B. The dot product can be calculated as follows. So you can see that we are taking the one, this is the A1, and we are multiplying it with B1. So it is this one. So B1. B1 is equal to 4. A1 is equal to 1. So it is this one. We multiply the 2, and then we go to the next sum. So here I will write it down actually underneath to make it easier. So this is A1. This is A2. This is A3, as you can see. And this is B1, B2, and B3. So taking A1, B1, adding A2, B2, and adding A3, B3, we are getting the dot product, which is equal to 4 minus 6 plus 5, which is equal to 3. So if you did a calculation or you use a calculator, you will find out that the dot product that can be described by this formula, which is very similar to what we have seen in here, only n is equal to 3, we are getting that the dot product of the vectors a and b in R3 is equal to 3. So let's now look into another example where we will do all the calculations manually step by step. So we have these two different vectors. We have vector a and vector b. Let me also here the arrows. And I want to calculate the dot product a, b. So the ATB, the dot product ATB, is equal to, and we know that if we are in the n three-dimensional space, so we are in the R3, we expect that we will need to just use the cross product 3 times, and we need to add them up. So we know that it's equal to A1. Let me use the black color. So A1, B1 plus A2, B2 plus A3, B3. Now, what is A1, what is A2, and what is A3, and what is B1, B2, B3? So A1 is equal to minus 1, B1 is equal to 0, A2 is equal to 2, B2 is equal to 1, and A3 is equal to 2, this is 3, and then B3 is equal to minus 3. Now, what is this amount? Minus 1 times 0 is 0, 2 times 1 is 2, and then 2 times minus 3 is minus 6. And what is 0 plus 2 minus 6 is minus 4. So let's now understand what is this application of dot product and how it can be used. So the dot product between these two vectors gives us an idea, a way to measure their similarity. So it combines the magnitude, the length of the vectors, and the cosine of the angle between them. In simple terms, it tells us how much one vector extends in the direction of the other one. Now we know how we can calculate it. Once we have the vectors, we understand the notation. We also know this relationship between the vector and the distance, what we mean when we have norm. When we have a distance, we also know the length of a vector. I want to combine all this and combine this with this idea of cosine, which is something that we'll learn in our high school as part of also trigonometry and geometry. I want to relate this all to make a sense how geometrically we can interpret this idea of dot product, and it will all make much more sense. So the dot product between the two vectors gives us a measure of their similarity. This is something that we are also using a lot in the field of artificial intelligence when we want to compare two different, for instance, users. So we have one user and we want to compare this one user to the other user. Then we are using this cosine rule. We are using what we call cosine similarity as a way to measure their similarity. So how similar those two customers are, how similar those two users are, how similar those two companies are. And we are doing that by using this simple cosine idea, which also is related to this idea of norms, this idea of distance, or the length of a vector, and the relationship between two vectors. So let's actually wrap this up together and clearly indicate what is this relationship between the dot product, the length of a vector, cosine rule, and this cosine similarity. So in simpler terms, this dot product, it tells us how much one vector, it extends in the direction of the other one. So when vectors point in the same direction, then we know that the dot product is positive and largest. It means that we are dealing with two vectors that are very similar. But when the vectors are perpendicular, then the dot product is 0. And we say that those two vectors do not share any direction. They are not similar. So when the vectors point in the opposite direction, then the dot product is negative. We are saying those two users are really negatively correlated. So one is the opposite of the other one. so to say. So let's actually plot this and see it and bring them all together. So let's say we have a vector S and we have a vector R. And we want to see how similar the two are. So we have here our vector S, and here we have our vector R. And those two vectors come together and they create this angle. And we are referring this angle by angle theta. This is just a way to refer to our angle. Those are all things that we learned as part of high school trigonometry, so this should all seem very familiar. So from the geometry, we know that if we have this triangle, and here we got this angle, which is theta, and here we got, let's say, side C, and then here A, and then the B, we know that the C squared is equal to A squared plus B squared minus 2 times A times B times cosine of the opposite angle of the C, which is theta. Now, let's actually go ahead and apply this to our case when we, instead of having just a triangle, we got a vectors. So we got a set of 3 vectors that form this triangle. And we already have seen in many examples previously one way of doing that. And let's actually go ahead and transform this vector, into vectors. And we can do that if we plot in here this side, then this. So we basically recreate the same triangle, only this time the sides are just vectors. So this is, let's say, our vector R, this is our vector S, and then this is obviously the R minus S. And the opposite side is alpha. So the vector R and vector S, they form the angle alpha. So when we apply to the cosine rule to this, of course, we, instead of using vector notation, we need to use their distances, because the cosine rule is based on the sides, so the length of the sides. So the length of this side, this one, we denote by our common notation of the norm, which is simply this thing. And then the same holds for this side, which is simply the norm of vector S. And then for the third side, for this one, we then have norm of R. So if we apply this cosine law to our specific example, we can see that in our case, our C squared is simply the length of our vector R minus S only squared, which means that, so let me actually write it down for simplicity, that part. So A is then, in this case, my vector R, and then the distance of it, obviously, so the length of the vector R, and then B is the length of vector S, and then the C is simply equal to the length of R minus S. Then here I will just change my angle and I will call it theta. And let's now apply the cosine law to our actual example, which means that we got R minus S and then squared is equal to, and then we got R squared and then plus S squared, so the length of the vector S and then squared, minus 2 times R times S times cosine of theta. So one thing that we can recognize here very quickly is that here we are dealing with the squared of a length of a vector R minus S. And we have learned from the previous definition of a dot product of a vector with itself, so the dot product of vector V is equal to the squared of a distance. So this means that here we already got the squared of a distance of the vector V. So this is something that we have because we have R minus s and then squared. This is exactly the same as the vector v and then squared with its length. So the length of vector v squared is the same as the length of the vector r minus s squared, because in this case the v is equal to, so the vector v is equal to vector r minus s. And from this we can see that this means that here we are dealing with the dot product of r minus s. So let me actually write this down in here in our example. So this is basically the right-hand side of the formula that we saw before, where it was saying that vector v dot product of vector v, so this is equal to, and then vector v, the distance of or the length of it, and then squared. So in this case, the vector v is equal to r minus s. This means, knowing this, we can actually make use of that formula and say that here we are dealing with the dot product of r minus s, which means that we can write that this can be rewritten as r minus s and then times r minus s. So in the left-hand side, we will start working with the dot product with the vectors, while in the right-hand side, we will still keep our lengths. So here we have the length of the r vector, so r squared plus s squared minus 2 times r, and then s, and then times cosine of theta. Now, let's actually open those parentheses. So this gives us r, and then r, basically the same dot product of vector r, and then minus s r, so dot product of vector s and r, and then minus s, actually plus s, and then s, and then minus s times r. So I'm basically opening the parentheses of the above part, this left-hand side, to simplify it. And then in the right-hand side, I will just copy-paste this. So r, and then squared plus s, and then squared, and then minus 2 times r. Forgot here the arrows. And then s, and then cosine of theta. Let me actually go ahead and remove all these parts to open up some space for us. And there we go. Right. So let's actually go ahead and simplify what we got here. Now, what do we see here? We see here that here we got one dot product, and we know that the dot product of a vector, RR, is simply the distance of that vector and then squared, minus here we got, so we will just keep it like that. We are taking the dot product of vector S with vector R. We are adding here we again got a dot product of a vector with itself, which is equal to the length of that vector S, only the square of it, using exactly the same law that we just saw, the dot product of a vector, and then here minus, and I will keep the dot product of these two vectors S and R together. So this is then equal to, and I will just take over this part exactly as it was. So R and then squared plus S and then squared, and then minus 2 times R and then S and then cosine of theta. Now, we already see a couple of things that we can cancel out, which is great. So we see here that we are dealing with the length of a vector R and then squared, something that we see here too. So we can safely cancel those out. Another thing that we can see that we can cancel is this. So again, the length of the vector S and squared. So this also go away. And we end up with this much more simpler formula. So we got minus S and then R, and then minus S and R. And then this is equal to minus 2 and then R, and then S, then cosine of theta. Now, we already see that this, we can combine, we can say this is equal to minus 2 times, and then the order doesn't matter, of course, in the dot product. So R and then S, and then this is equal to minus 2 times, and then the distance or the length of the vector R, and then the length of a vector S, and then times cosine theta. Okay, perfect. Now we can get rid of minus 2 too. So let me clear some space up to see what we end up with. So we are left with the following formula. So we see that R and then S, so the dot product of these two vectors, is equal to R, so the length of the vector R, multiplied with the length of vector S, multiplied by cosine and then theta. So this is basically what we end up with and exactly what we wanted to prove. We wanted to see that the dot product, so this is the dot product of vectors R and S is equal to the length of the vector R multiplied with the length of a vector S multiplied by the cosine of this vector that they are forming, so cosine of theta. Now, why is this important? This means that we can also take this cosine, bring it to the other side, and we can use that to describe the cosine with this dot product as well as the length of these two vectors. So from here, we can say that the cosine of theta is equal to the dot product of the vector R and S divided to the length of vector R multiplied with the length of vector S. So using this, we can then calculate the cosine similarity between two different vectors, and this then helps us to mathematically compute what is this measure of similarity between two different entities. Whether we want to compute similarity between two customers, whether we want to compute the similarity between two users, similarity between two profiles of clients. So this can be applied really to do very large range of applications. But the idea is that in this way we have proven that we can use this algebraic concept, the linear algebra concept of the dot product, in order to compute a similarity measure that will help you to compute the similarity between two different entities. And this is a very common application in machine learning, in artificial intelligence. The cosine similarity is one of the most popular similarity measures that is used in data science, in machine learning, in artificial intelligence, whether it's in the clustering algorithms like k-means, whether it's in different sorts of machine learning algorithms, or just in general to compute the similarity between two reviews that customer leaves, similarities between two profiles of customers, similarity of two different users. For instance, two users that are watching movie and you are building a movie recommender system, you can use cosine similarity to compare the two users' behavior in order to improve the quality of the movie recommender. And the applications are so versatile that my takeaway would be to just keep this cosine similarity in mind, the formula of it and how it is related to the dot product, because this is something that will be very useful for your journey in applied sciences. Let's now talk about the idea of inner product and how it relates to the idea of dot product. So by definition, the inner product generalizes the dot product to more abstract vector spaces, which can include spaces with complex numbers. So it retains these key properties like linearity, linear independence, and the notion of angle and the length that we saw before, the norm, and how we relate it back to cosine similarity for much more complex vectors. The inner product involves basically conjugating one of the vectors. And in real vector spaces, the inner product is simply the dot product. So if we have vectors that are from real spaces, so they are from R2, R3, then in this case, the inner product is exactly the same as the dot product. So let's now move on towards one of our final topics as part of this unit. And this is a very important topic, very often referred as Cauchy-Schwarz inequality. So this inequality and the law states that for all vectors x and y in an inner product space or dot product space, the absolute value of their inner product is less than or equal to the product of their norms. Mathematically, we can express this as the following expression. So where this part, it simply represents this dot product of x and y. And here, as we already saw before, the x, and with this specific notation, it refers to the length or the norm of our vector x, and then this one, the norm of a vector y. So this definition should, and this way of referencing the norm and the length as well as the dot product should seem very familiar to you. So what we are saying here is basically, if we have a vector x and the y, and we have a dot product of x and y, if we take the magnitude, then this will be smaller than equal the length of the vector x and the length of vector y. So the intuition behind this law is that it tells us that the absolute value of this dot product between two vectors cannot exceed the product of their lengths. So basically, if we have a vector A and vector B, and we are computing the dot product between them, so ATB, then this amount will always be smaller than equal than the length of vector A multiplied by the length of vector B. This is all what this law is about. So this inequality, it tells us that the absolute value of the dot product between two vectors cannot exceed the product of their lengths. So let's actually look into and understand why does this even make sense. So this idea, this inequality, Cauchy-Schwarz inequality, it is about the limits of similarity. So what is this level, the maximum level that we can have when it comes to the similarity of two entities? For instance, if we got two users and we want to understand how similar those users are, this inequality helps us to understand what is this maximum level that we can have when it comes to the similarity of these two people. What is this maximum similarity measure that we can have based on the characteristics of these users? So no matter how similar the two vectors are, there is an upper bound to this measure based on what kind of vectors we are talking about. And this maximum amount, this maximum measure, is defined by their lengths. So it confirms that this cosine of an angle that we just saw, because we saw that the cosine theta is equal to, it's exactly what we got in here. So we saw that cosine of theta is equal to the dot product of vector r and s divided to the lengths of them. And that's exactly what this Cauchy-Schwarz is basically saying. It's saying that it confirms that this cosine of the angle between them, between these two vectors, part of this dot product calculation, it cannot exceed 1, which fits to our understanding of the cosine, because we know that cosine is a value that should be between -1 and 1. To be more specific, -1 and 1 included. And knowing this helps us to get a limit on this idea. So how can we prove the Cauchy-Schwarz inequality? This comes down to this formula that we have already proven. So let us actually go ahead and prove this Cauchy-Schwarz inequality. It's quite straightforward. So we have just learned, and we have actually proven, that cosine theta is equal to R and then S, if those are our two vectors. And then here we got the length of the vector R and then the length of a vector S. Now we know that a cosine is a measure that will always be between -1 and 1. So this means that we can use in order to prove this. So knowing that this value will always be smaller than or equal to 1, it means that we can just take this and we can bring it here. We know that the lengths are both positive amounts, so it means that I can just multiply both sides by this amount. That means that I will be left with R and then S, so the dot product between the two vectors, that will be smaller than equal, and then R, the length of this vector, multiplied by the length of the vector S. Now, as you can see, this is exactly the Cauchy-Schwarz inequality that it says, because it says that the absolute value of the inner product is less than or equal to the product of their norms. So the Cauchy-Schwarz inequality is a fundamental principle in mathematics, but also just in general it's used in so many applied sciences. And it's applied across various domains, including linear algebra, physics, but also machine learning and in finance. So this helps us to establish a limit on the correlation or this idea of similarity that can exist between two vectors in any inner product space. So if we got two different companies and we want to understand how similar they are performing, by knowing their performances and their measures, we can then have a limit on how similar the two companies can be, or how similar the two users can be based on their previous history. And this all is being done by using this idea of Cauchy-Schwarz inequality. Now, why does this matter? So understanding this inequality gives us deeper insights into the vector spaces, especially when working with this high-dimensional data, which is quite often the case when we are dealing with transformers, with large language models, with deep neural networks, or we are working in finance. So this is a super important concept when it comes to applied sciences. So it ensures that this validity of operations when it comes to the mathematical side and the transformations we perform on our data on the practical side, that those two are coherent. And we ensure that we are safe in making different assumptions, and we provide in this way the safety net for our design of the algorithm. We ensure that our algorithm is performing well. So every time when we are creating a program or an algorithm for a specific case, then using this inequality, we can basically add use cases, we can create a test cases, and we can add these constraints to our algorithm, and we can design our algorithm in more intelligent way. And we can ensure that we won't have cases when the limit goes above this threshold that we already got based on this inequality. And this is a very important application in a practical sense when it comes to applying linear algebra into applied sciences. Now, the final question that I will leave you with is the case when the norm is equal to 0. So we briefly touched upon this point, and we spoke about this idea of perpendicularity, and in one specific case when the norm of a vector v equals 0. So the theorem says that the norm of a vector v equals 0 if and only if v is the 0 vector. So mathematically, this means that the distance of the vector v is equal to 0. So basically, we are dealing with a 0 vector. So v is equal to 0. This means that the only vector with no magnitude pointing in no direction is the 0 vector. Only in that case we will get a norm equal to 0. This concept is super important to understand this uniqueness of a vector and these different foundational principles and properties that we'll also see appearing in the upcoming lectures and in the upcoming lessons. This is all for this module and for this unit. We have learned a ton of important stuff when it comes to the vectors. So we have looked into from very scratch, the idea of vectors, the norms, the distances, the inner product, the dot product. We have looked into the geometric interpretation of it. We have visualized it. We have looked into different properties of vectors, the spaces. We have also looked into the properties of the dot product. We have proven them. We have looked into a ton of examples. We have understood how we can plot vectors, how we can understand and relate this idea of vectors to this dot product and the dot product to the cosine of two vectors and the cosine of an angle and the relationship between two vectors and the similarity between these vectors, how we can use and apply that in machine learning, in artificial intelligence. We have kind of made those relationships there too. And we have also looked into fundamental concepts, including the scalar vector multiplications, operations with vectors, adding them, subtracting them. And we have also looked into this idea of linear combination, the span of vectors, as well as linear independence. We have defined linear independence, and we have also spoken about and provided examples for vectors that can be marked and defined as linearly independent, and also examples when our vectors were linearly dependent. Thanks for staying with me so far, and I will see you in the next unit. Welcome to the Module 1 of this new unit, when we are going to talk about matrices as well as linear systems. So those are all fundamental concepts that you will see time and time again when applying linear algebra, not only in mathematics, but also in applied sciences like data science, artificial intelligence, when training different machine learning models and trying to see what is this mathematics behind machine learning models, different optimization techniques, when you want to solve different problems using linear algebra. So in this first module, as part of Foundations of Linear Systems and Matrices, we are going to introduce this concept of linear systems. And then we are going to talk about the general linear systems. We are going to see this common labeling of the coefficients, this idea of indices that refer to the rows and the columns. We are going to see what is this differentiation between homogeneous and non-homogeneous systems. So without further ado, let's get started. So the linear systems form the bedrock of linear algebra, modeling this array of problems. Thanks to these advancements in these linear systems and solving it in computing, we can now solve a large amount of problems in a very efficient and a fast way. So the general linear systems can be represented by this set of m equations with n unknowns. In the previous unit, when we were looking into this linear combination of vectors, we saw this notation, which was A1, and then we had C1 multiplied, or rather, let me keep the same notation. So we had this linear combination of vectors. So we had beta 1, and then we had A1 plus beta 2, and then A2, and those are all vectors, plus A3, so beta 3 times A3, dot, 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 and then beta m times am. This is the notation that we saw before, and we said we wanted to come up with the linear combination of these different vectors A1, A2, A3 up to am, and then we use that in order to get a sense of whether we are dealing with linearly independent variables, vectors, or linearly dependent vectors. And then we also commented on the span that these vectors take. Now, when it comes to the vectors and just in general linear systems, we can represent what we had before now in terms of with a bigger system. So in terms of m equations and with n unknowns. So here what you can see here is that we have m different equations. So we have beta 1, b1, b2 up to bm. So you can see it in here. And then each of these equations, it contains n unknowns. So you can see that the unknowns, it stays the same. So the unknowns are those x1, x2 up to xn. So x1, x2 up to xn are the set of all n unknowns. And then m equations that you can see in here are all these equations. So a11 x1 plus a12 x2 ... and then a1n and then xn is equal to b1. And here, one thing that is really important to keep in mind is that the indexing is what we need to focus on. So we need to keep this one in mind, this aij and this xi. So this is something that we also spoke about when discussing the linear combination of vectors. We slightly touched upon on this topic. So let's now dive into this indexing. And how do we index this A, I, J? What are these A's? What are these J's? And here you can see that we have A11 and then A12 and then up to the A1n. And this is in our equation 1. And then we have in our equation 2, A12. Let me actually write this with a different color. So in our equation 2, we got A21, A23 up to A2n. And these A's that you see here, those are just real numbers. So A11 can be 1, A12 can be 3, A1n can be 100. And then the same also holds for this B1, for this B2, and for this Bm. And all these values, A's and B's, they are just real numbers. The only unknowns that we got here are those. So the x1, x2 up to xn. All right, so what about the indexing now? So we got A, I, J, and as you can see, in this case, the first thing that we can see here, it stays everywhere the same, which is the 1. So we got here 1, we got here 1, and up to the point we got here 1. Whereas the second index, this one, it does change. It grows gradually with 1, and it goes from 1 to 2 and up to n. So you can see here that the first index or index I, it goes from 1, it doesn't change, it's just 1. So it is 1, 1, and 1. So here, in all cases for this equation, I is equal to 1. But another thing that you can notice here is that the index 2, unlike index I, so the second index, which is the j, so you see here that the second index is referred as j. This is a general way of defining the indices. So here, j is equal to 1, 2, ... and then n. So basically, the I doesn't change in the same row, but the j changes. And then, of course, we have slightly different in terms of I, but then the same for j for our second equation. So here, I is equal to 2, and then j is again equal to 1, and then 2, ... and then n. And then here, up to, for the last equation, our I is equal to m, and then our j is again equal to 1 till 2, ... So you might notice that I was looking at this from the row perspective. So I was saying per equation or per row, the I doesn't change, but then the j stays the same, and then it is either 1, 2 up to n, but the set is the same. So it contains all these different elements here. So 1, 1, 2, and then n. But it contains all these different real numbers going from 1 till n. Because we are combining and we are creating this combination, the sum of all these values, a1, 1, and then x1, a1, 2, x2, a1, n, xn. And another thing that you can also notice here is that here with the second index, so with this j is equal to 1, then here the x's corresponding index is also 1. When the j is equal to 2, then the x's corresponding index is also 2, and then here the same story. And you will notice that while the coefficient contains two indices, 1, 1, 1, 2, or 1, n, which are the two indices for the coefficients, for the unknowns, we got just single index, which goes from 1 till n. So basically, for a's, for the coefficients, so I, let me write with the right color. So I can be 1, 2, all the way to m, whereas in case of j, it can be 1, 2, all the way to n. And the indices are basically used to help us to keep track of in which row we are and what is the variable that the coefficient belongs to. Because knowing this second index, this helps us to understand that we are dealing with a coefficient that corresponds to this first unknown, the first variable x1. And then the same holds in here. As you can see in here and in here, we are dealing with the same variable x1. Therefore, the second index, the index j, is then the same both in the first equation and in the second one. In both cases, it's equal to 1. Okay, so now when we are clear on that, let's also understand this high-level concept, because you will see this system of linear systems, this m equations and n unknowns, appearing a lot not only in terms of calculating and finding the solution to this linear system, but this actually has a very common application when it comes to running regression, linear regression specifically. And one thing that you can notice here is that here we got also this b1, b2 up to bm. And you will notice that here the index also goes from 1, but then this time to m. So when it comes to the rows, we have m rows or m equations. Therefore, we also expect when it comes to counting from the top that at the bottom we will see an m. Whereas if we count from this side, so kind of like, imagine it like a column, then we see that it goes from 1 till n. So those are common abbreviations and reference to number of observations and number of features that you will see in your data when dealing with data analysis or modeling data. So just keep those things in mind, this abbreviation of m and then n, m equations, n unknowns, because this will become very handy. And the same also holds for this indexing. Just to keep in mind that this I and this j, what those indices are, and how, for instance, the first, the first index changes when we go from up to the bottom, and how the second index j goes and it changes when we go from left to the right, when we go through the columns. But we are going to see this also in the upcoming slides, so we will have time to practice it. So this is what we are calling a coefficient labeling. The coefficient a, I, j, so this thing, in a linear system, they are labeled where the first index represents the row and the second index denotes the column. So when we see Aij, we know that this refers to the row and the j refers to the column. So this is something that we use in order to understand where exactly in our matrix, something that we will see very soon, where exactly our unit or our member that is part of our matrix, where exactly is that located, in which row and in which column. The systematic labeling is super important because this helps us to keep the structure, and this helps us to understand what does this coefficient represent. What is this row that it belongs, and what is the column it belongs. So for which equation and for which unknown we have already solved the problem, such that we can know what this coefficient represents. So before moving on to the actual linear systems and this definition of matrices, let's quickly understand this distinction between homogeneous and non-homogeneous, because this will help us to also get an understanding how we can solve a system of linear systems. So a system is homogeneous if all the constant terms bi are 0. Otherwise, it's non-homogeneous. So identifying this helps us to really understand the nature of the solution set that we need to get, and to understand what kind of strategy we need to use in order to solve this problem. Now, what do I mean by bi? We just saw that we had this system of m equations with n unknowns. And we saw that we have in the right-hand side this b1, b2 up to bm, which means that we had this m different equations with n different unknowns. And to find a solution to the system, it means finding these values corresponding to x1, here x2, xn. So basically finding the set of x1, x2 up to xn that solves this problem. And for us to know how to solve this problem, we need to know whether this b1 is equal to 0 or not. This b2 is equal to 0 or not. And then this bm is equal to 0 or not. This is very similar to this idea of solving any sort of problems that contain unknowns. For instance, if we have 3x is equal to, let's say, 5, solving this is entirely different than if we know that the 3x is equal to 0. So this is a super simplified version, of course, but the idea is the same. Knowing that this b1, b2 up to bm, these are 0, this gives us an idea how we can solve this problem. And later on, we will see this distinction between non-homogeneous and homogeneous system. And whenever these b's, so whenever this b1, b2 up to bm, whenever these b's are 0, then we are saying that the system is homogeneous and we need to solve a homogeneous system. Otherwise, we are dealing with non-homogeneous system. So this means that the bi's are not all 0. Let's now move on to the second module, which is about the matrices. So we are going to define the matrix. We are going to see the definition of it, as well as the notation, this idea of rows, columns, dimensions, some of which we have already touched upon, but we are going to go into the depth of it. We are going to learn properly, as well as we are going to see many examples. Then we are going to talk about matrix types. So here we will talk about identity matrix, diagonal matrices, and also special type of matrices, like matrices containing only zeros and only ones. So by definition, a matrix is a rectangular array of real numbers that are arranged in rows and in columns. For example, an m by n matrix A can be represented as follows. So let's look into this definition and this reference to matrix. We call this matrix or matrix A, and every matrix, it can be described by these rows and columns, where we always have this way of describing this matrix always should be defined by the number of rows and number of columns. So this is super important. And let's look into this specific matrix. So we have a matrix A, and all these values, they are members of this matrix. They form the matrix. And we already saw this labeling of A, I, J, where we said that I is referred to the row. So you might recall that those were all these equations that we got. So this horizontal lines where I was equal to 1, I was equal to 2, I was equal to 3, up to the point of I was equal to M. And then we had the J, so this thing, and then J was referred to the columns, and we had J was here 1, and then 2, and then 3, up to the point of N. So 1, 2, 3, and N. This is exactly what you can see here. So in this matrix, we got all these elements. A11 is a number, A12 is a number, up to the A1n is a number. Those are all real numbers. And one thing that you can notice here is that here we got A11. So this is our first row and first column. Here we got A12. This is our first row and second column. And then we got up to the point of A1n. Actually, let me just write this down even at a bigger scale such that I can make more notes. So let's assume we have this matrix A, and this matrix A even bigger, and we got all these different elements. So we start with our first row, and here we have A1, 1. So here, the row that I will write with, let's say with blue, the row is equal to 1, and then the column is 1. So this is row 1, this is row 1, row 1, and this is column 1. Let me write it with red. This is column 1. This is column 2. This is column 3, ... and this is column N. And this is row 2. This is row 3, ... and this is row M. So in total, I got M rows and N columns. I will come to this notation that I'm putting here later. For now, let's keep track of the rows and the columns to get a good understanding what these indices were about that we just learned. So every time I will also mention this reference to A, I, J to keep track of this. And also let me write it with the right colors. So A, I, this is the row, and J, which is the column. So all the elements I'm just defining by this A because it's just a way to reference a part that comes from a matrix. It's just a common way to write the entire matrix by a capital letter A, whereas its members we will write with the lowercase a. So this is matrix A. All right. So here in the second row but first column, we got A, 2, and then 1 because it is still in the first column. And then when it comes to this element, we have here A. The row is the first one because we are in the first row. But then we are in the second column, so this one should be 2. Then we go on to the next element in our first row, so A1, and then 3, and then ... And the last element is an A. As we are still in the first row, it will be 1, the I. But then given we are in the last column, the column index, or the J, will be equal to N, because we got in total N columns. So we are now ready to go on to the second row. So here, given that we already have our first element, A to 1, this is in our second row and the first column. So the I is equal to here 2 and J is equal to 1. Let's now write down the element in the second row and second column. As you might have already guessed, I is equal to here 1, I is equal to here 2, and then the J is equal to 2. And then we go on to the next element, which is in the second row and the third column. So it's A, the row index is 2, so I is equal to 2, and then the column index is 3. And then we got A, as we are in the second row, it is the I is equal to 2, and as we are in the last column, the J is equal to N. Now you might have already guessed when I was writing this down that whenever you are in the row and you move on to all the elements in the same row, the I, so the row index, it stays the same, only you need to update the column index. So here, for instance, you got 1, 1, 1, here also 1. So all the way down in the same row, or 1, which logically makes sense because we are in the same row. So the row index should not change, but instead you should change the column index, like here. Column 1, column 2, column 3, all the way to column N. So those are our columns. So let me make this distinction. And those are our rows, as you can see. So this kind of mentally helps us to understand why we are writing all these indices. Over time, once you practice more with this will become more natural. Very quickly remove this. So now I will write the rest very quickly. So as you might have already guessed, we are in the third row. So we have A3. So everywhere I will just write down the A's. So first I will write down the A's, and then the rows. The row index will stay the same as I am in the same row, but then I will increase the columns gradually. So we are in the column 1, and then column 2, column 3, up to the column N. So now, the remaining stuff you can actually write down yourself to just practice. Let's now move on to the last row and last column. So in the last row, we got A, up to here. And in the last row, the row index is M, which means that here I need to have M, everywhere I need to have M. And then the column index is 1, 2, 3, all the way to N. So this last column is very interesting too. You can see here that we have the opposite of what we have here, because in the last column, we see that the column index is the same, so it is everywhere N. Only the first index, the index of the row, it changes. It goes from 1, 2, 3, up to M, which is of course logical because we said that in the last column, if we are looking at it from the perspective of a column, so all these values, these A's, so all the N's, they are logical because we are in the last column, we are in the same column, but then the row changes. Here we are in the row 1, here we are in the row 2, row 3, up to row M. Therefore, we have also at the end A, M, N. Now, let's talk about this idea of M, N. We said that our matrix A has M as a number of rows and n as a number of columns, which you can see, by the way, also here. So we always refer the dimension of a matrix. So the dimension of matrix A by these two numbers. So first we always write down the number of rows, in this case m. Then as the second element we are writing the number of columns, in this case n. We are always putting this small x in between to kind of emphasize m by n matrix, and we most of the time use the square braces to showcase that we are dealing with dimension. And in this case, we are saying the dimension of matrix A is equal to m by n. So we are dealing with m by n matrix. This is a common convention used in linear algebra, in mathematics general, but also used in data science, in machine learning, artificial intelligence. So whenever you are dealing with matrices A, it is a common convention to talk about this idea of dimensions. And the idea of dimensions is super important when it comes to the idea of multiplication, multiplying vector with matrix, matrix with matrix. So this dot product, dimensions play a central role in here. So keep this one in mind. Once we get to the point of dot products, this one will become very handy. So let's now look into a specific example where we see simple matrix A. So in this case, you can see that we are dealing with a matrix that has a 2 by 3 dimensions. So like we just learned, 2 by 3 means that we got 2 rows and 3 columns. That's something that you can also see here very quickly. So you have a small matrix. On the small matrix, it's really easy to actually count. So you can see that we got row 1 and row 2, and we got column 1, column 2, and column 3. So this basically confirms these dimensions. Therefore, we are also saying that we have a 2 by 3 matrix. And like usual, we first write down the number of rows and then the number of columns. You can see here that here we have these elements for our matrix. So A is equal to 1, 2, 3 for the first row, and then 4, 5, 6 for the second row. So from this, actually, I think it's a good exercise to just verify our understanding of indices. And from this, we can write down that, for instance, all these different elements, like A11 is equal to 1, A12, which means that we are in the first row and in the second column. So we have this element is equal to 2, and then we got A and then 1, 3. So we are in the third column. So this one is equal to 3, and then A21 is equal to 4, A22 is equal to 5, and then A23 is equal to 6. So this is actually a good way to practice our understanding of indices, our understanding of this matrix structure, and the understanding of dimension of the matrix, which in this case is 2 by 3. So this is yet another different definition of a matrix structure when it comes to the rows, columns, and dimensions. So this is exactly what we just spoke about on our example. And let's just quickly look at the formal definition. So the rows of a matrix are the horizontal lines of the entries, while the columns are the vertical lines. So basically it's saying those are, let me remove this. So the rows are the horizontal line, and the columns are those vertical lines. Those are the columns. This helps us to form these columns. So column 1, column 2, and column 3. Whereas these horizontal lines, it helps us to create the rows. So row 1 and row 2, which is the core matrix operations. So when it comes to matrices, we often perform matrix additions, matrix subtraction, but also matrix, a scalar multiplication of this matrix, so multiplying matrix with a scalar, and then matrix multiplication just in general, so taking two matrices and multiplying them. We are going to look into this concept in detail. We are going to see many examples like before. We are going to dive deeper into this such that we lay the ground on to the next module, which is solving a system of m equations with n unknowns. So solving this general linear system. So for the beginning, we will be looking into this matrix operations where we are adding or subtracting matrices. So by definition, the sum of two matrices A and B of the same dimensions is obtained by adding their corresponding elements. So by taking the element ij from both matrices and adding them to each other. So in this case, you can see that matrix A and B are here. And the definition says we just simply need to take the corresponding elements from the row I and the column j, take them, add them, and this will become an element in our final matrix. Because when we are adding two matrices of the same size, the result is yet another matrix. So we will use the matrix A to add to matrix B, and this will give us a matrix A plus B. And this ij simply refers to the indices corresponding to the row and the column. We will look into an example in a bit, and this will make much more sense. And the same holds also for the difference. So by definition, the difference of the two matrices A and B of the same dimensions is obtained by subtracting their corresponding elements, which means that in order to obtain this matrix A minus B, this is a new matrix, we simply need to look for each element. So we are going to index them for a row I and j. We are going to do this pairwise, element-wise subtractions. We are going to see what is that element corresponding to the row I and column j in the matrix A, which we say is Aij. We are going to subtract from this the element in the row I and column G that comes from matrix B. And this will give us our new matrix, which is A minus B. So let's now look into an example. In this matrix A and matrix B are used, and matrix A is of the size 3 by 3. Matrix B is of the size 3 by 3. In order to obtain A plus B, what we are doing is that we are performing element-wise additions. Now, let's verify this. So, what we are doing here is that we are saying A plus B. Let me actually get a larger area here. So, let's say we have the two matrices. I want to add the two in such a way that we do everything one by one, such that this idea of A plus B and addition of the matrices will make sense. So we want to find out A plus B. For that, what we are going to do is that we are going to make use of this definition that A plus B and then Ij is equal to A Ij plus B Ij, which is a fancy way or mathematical way or describing that for each element we need to go and look for the row I and column j and take that element from the matrix A and from the matrix B. So this means that for A plus B, this is going to be a matrix that will have the same number of rows and the same number of columns as two matrices, because both A and B are 3 by 3, which means also their sum is going to be 3 by 3. So this is going to be 3 by 3. And here we are going to take for the first row and the first column, so for A plus B, 1, 1, so first row and first column, we need to go to the first row and first column of matrix A and the first row and first column of matrix B, and we need to add these two elements. So we need to do 1 plus 1. And then we need to go on to the second column. So the first row and the second column, which means that we need to be here in both matrices. So here we have 0 plus 2. And then we got 2 plus 3. And then we got 0 plus 0. So you can see it in here. And then we have 1 plus 0. And then we have 3 plus 1. 0 plus 1. And then 0 plus 2. And then 1 plus 3. Which gives us... So 1 plus 1 is equal to 2. 0 plus 2 is equal to 2. And then 2 plus 3 is equal to 5. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 0 plus 2 is equal to 2. And then 3 plus 1 is equal to 4. 1 plus 3 is equal to 4. Which means that our A plus B is equal to this matrix that we got in here. So you can see that we are getting exactly what we have here. Only we have done it manually, one by one. So the same idea holds exactly when we have A minus B. Only instead of adding, you will have to do here minuses. So minus, minus, so everywhere minus. So 1 minus 1, 0 minus 2, 2 minus 3, etc. So let's look into another addition. So in this case, by definition, it is defined as this element-wise of the adding of these two matrices. Here, the only difference in this definition is that it's calling this A plus B as C. So this new matrix that we are getting as a result of adding A to B, it's calling C. So basically, it's the same as calling this matrix as C. You will see also this type of definitions. So in this case, the matrix C is equal to A plus B, which basically means that for each row with index I and with each column with index j, go and look for row I and index j, take the corresponding elements from matrix A and matrix B, add them in order to get that corresponding element in our new matrix C. And you can see that in this example, that's exactly what we are doing. We have A, we have B. We are taking this element and this one, so 1 plus 1, we are getting here 2, and then 0 plus 2, we are getting 2 here, 2 plus 3 is 5, and then 0 plus 0 is equal to 0, 1 plus 0 is equal to 1, and then 3 plus 1 is equal to 4. So now we already go to the next topic, which is about scalar multiplication of a matrix. So by definition, scalar multiplication of a matrix A by a scalar alpha results in a new matrix where each entry of A is multiplied by alpha. The idea of scalar multiplication in matrices is actually quite similar to this idea of scalar multiplication in vectors. So we have already seen in the lecture of the vector multiplication that when we were having this scalar C and we had this vector A, then when we are multiplying C, which is a real number, with vector A, then we simply need to take all the elements of vector A, so A1, A2, all the way down to AN, and we need to multiply them by this same scalar, so C. This is what we were doing with vectors. And that's exactly the idea behind matrices. And when doing the scalar multiplication of matrices, only instead of multiplying only just one vector with the scalar C, now we need to apply this to all the rows and all the columns. So here we got this one column, and matrix is simply a combination of multiple vectors, which means that we need to multiply all these elements of all the vectors, of all the columns in this matrix. So let's actually look into a specific example. So in this case, we have a matrix A, and this matrix A is this thing. And we have a scalar, which is 3. So in here, our alpha is equal to 3, or you can call it C or anything. So you can see that when we are scaling the matrix with a scalar, in this case 3, with this matrix, what we are doing is that we are simply taking each of these elements and multiplying it with the scalar. So 1 by 3 is 3, 2 by 3 is 6, 3 by 3 is 9, and 4 by 3 is 12. This is the idea behind this entire scalar multiplication of a matrix. In more general terms, if we, for instance, have a matrix A, so let's actually look into a high-level general example when we have the A matrix m by n. So we got m rows and n columns, and we want to get a scalar multiplication of this matrix. And scalar that we have here, as in our definition, it is defined by this alpha. Alpha is just a number. You can call it C, you can call it B, anything. So in this case, our scalar alpha is coming from R, so it's a real number. So alpha times A is then simply equal to this new matrix where all of these elements are simply multiplied by this scalar. So I will just take over all these values, H1 up to AM1, and then A12, A22, all the way down to AM2. And then let me also add the last column, just for fun, here A to N, and then here AMN. So here, this new scaled multiplied, so scaled matrix A, so alpha times A is simply equal to alpha times, so all these elements are simply multiplied by this scalar. It is as simple as that. So that's the simple idea behind matrix scaling. So when you are doing scalar multiplication of this matrix, you simply take all the values and you multiply them element by element, per row and per column, by that single scalar alpha. Do you know that you are multiplying them all without exclusion with exactly the same number, which is that alpha? So let's now look into the definition of matrix multiplication. So here we are no longer multiplying a matrix with a scalar, but we are multiplying matrix with a matrix. So the product of an m by n matrix A and an n by p matrix B results in an m by p matrix C, where each entry Cij is computed as the dot product of the each row of A and the jth column of B. Now, what does this mean? Firstly, let's look and unpack this part of the definition. So we got matrix A that is m by n, and then we got matrix B, which is n by p. What this means is that in this case, matrix A has m rows and n columns, and matrix B has n rows and p columns. So this is then simply the dimensions of these two matrices. So then it's saying that by definition, the product of these two matrices, so the product of A and B, the product of the two, B is equal to this matrix C. And each entry Cij, so Cij is computed as the dot product of the each row of A and the jth column of B. Now this part might seem a bit difficult, but once we look into the actual example and we illustrate this on our common high-level general expressions of matrix A and B and their multiplication, this will make much more sense. For now, before coming to this one, I just wanted to refresh our memory on one thing. I said before, when discussing also this idea of improving these different properties of vectors, that when we want to multiply a vector with a matrix, or a matrix with a matrix, or a vector with a vector, we need to ensure that from the first element, the number of columns is equal to the number of rows of the second element. This is also very important for this specific case and just in general for matrix multiplication. So you can notice here that the number of columns here is equal to the number of rows in here. And the order is very important. So in case of matrix multiplication, the order is really important, which means that if you have a matrix A and you want to multiply it with a matrix B, then the number of columns of A should be equal to the number of rows of B. Otherwise, you cannot multiply those two matrices with each other. So in case you got a matrix A that doesn't have the same number of columns as the rows of number of the matrix B, then there are some alternative things that you can do, including this idea of the transpose that we saw also doing when computing the dot product between this vector A and vector B. That's something that we also do in programming when we are dealing with this matrix and we want to compute this relationship between two matrices, but the number of columns of the first one is not equal to the number of rows of the second one. We are simply manipulating these matrices or removing some data. If that's not hurting our problem, maybe flipping, so transposing our matrix or applying any other source of operation to it to ensure that the two matrices that we are multiplying with each other, the first one's number of columns is equal to the second one's number of rows. So that's just the law, and that's something that you should follow if you want to multiply these two matrices. All right, so now let's move on to this idea of multiplying and the dot product. Let's look into a specific example, and this will help us to understand this process better. So before doing that, I just want to quickly show you this general idea. So if we have a matrix A that is m by n, which means that it looks something like this, like A1, 1, A2, 1, up to the point of AM1. And then here we got, let's say, A1, 2, A2, 2, up to the point of AM2. And then at the end we got AMN, and here we got A1N. So let me also add this one, 2N, and we got a matrix B. This matrix B is N by P, so it has N rows and P columns. So we are fine in terms of dimension here. And we got here B11, B21, up to the point of BN in this case. Let's not confuse the letters. So BN1, B12, B22, up to the point of BN2, because N now is the number of rows for matrix B, unlike for the matrix A, up to B1P, and here B2P, and here up to the point of B, and then NP. This is the last element. In order to perform multiplication between these two matrices, so to obtain a matrix C, which is equal to A times B, what we need to do is we simply need to take pair case, so pair row. For the row I, for instance, we need to take this element, so this row, and we need to multiply it with this. So we need to find a dot product between this row and this column. Then we need to move on to the next one, and then for the second element, we will then take this row and we will multiply it with this one. So this is then something that we need to do in order to obtain these elements. And you might have already noticed that we got this m by n and n by p. So you might have already guessed what will be the dimension of the C. If we got that the dimension of A is equal to m by n, and the dimension of B is equal to n by p, then the result matrix after multiplying the two, so matrix C, will be having a number of rows equal to this and the number of columns equal to this. So this middle part basically disappears, and the number of rows of the first matrix will be then the number of rows of this result matrix C, and the number of columns of the second matrix, so matrix B, will then be our final number of columns. So we will then have a matrix C that will have a dimension. So dimension of C will then be equal to m by p. So we will have m rows and p columns. So how we are going to compute this? So for Cij, which means row I and column j, let's look into the definition of it. It's saying Cij is computed as a dot product of the each row and the jth column. So each row from A and jth column of B. What is the each row of A? The each row of A is somewhere here. So each row of A, it is the A and then I1, then A, and then I2, and then A, and then I3, and then A, I, and then we got in total n columns. And we always do the transpose, right, when computing this dot product. So we then take the transpose. So we take this row I, and we multiply it. So we do the dot product between this one. This is the AI and the BJ. This is column J. It is somewhere here. So it is B, and then we got the first element, which is 1, and then J, and then B, 2J, B, 3J, up to B, and then in total we got n rows in B, so n, and then the J is the column, so it stays the same. So this is then the dot product between each row that comes from matrix A and the jth column that comes from matrix B. So it's always like that actually. So we always take row by row. So we take this different, so every time we take just a row and we multiply with the corresponding column, and then we get the dot product between this row that comes from the first matrix and then the column that comes from the second matrix in that specific order in order to get our dot product and that specific value. And what is this amount actually? So when we calculate this dot product, you can quickly see that we have I1 multiplied by B1J plus I2 multiplied by B2J, and then AIN multiplied by BNG. And this new matrix C will then have all these elements. So C11, C21, and then C31, and then C, the last row, as the number of rows of C is M, CM, see here, M. So C, and then here it will be 1, 2, C22, C3, and then 2, up to the point of CM, and then 2, and then here the last column will be C1, and then P is the number of columns in C, so C1P, and then C2P, and then C3P, and then C, M, and then P. Okay. So this is what we get. This is our final matrix C when multiplying matrix A and matrix B. So let me clean this up. C is equal to. Now, if you want to find out what is C11, you can easily fill in this general formula that we just calculated. The I is equal to 1 and then J is equal to 1. And this will give you C11 by using this formula. If you want to get the C and P, then just fill in the I is equal to M and then J is equal to P in order to get this value C and P. So you can already see the amount of calculations you need to do in order to get all these elements from these large matrices A and B. Let's actually look into a simple example to clarify this. So we have a matrix A here and matrix B here. And we want to do a multiplication of the two. And we have just learned how to do it. Let's actually do it one by one. So we got a matrix A, which is equal to 1, 2, 3, 4, with dimensions 2 by 2. Then we got a matrix B, which has values 2, 0, and then 1, 2. So it is 2 by 2. And I want to find what is C that is equal to A times B. And I know already by looking at these dimensions that C is going to be equal to 2 by 2. So you might recall that I said that when looking at this final result, the number of rows or the final matrix will be this. So the number of rows of the initial matrix A, and then the number of columns of this final vector C will be the number of vectors, number of columns of this second matrix B, so 2. Therefore, I know already before even doing calculations that the product matrix C equal to A times B is going to have a dimension 2 by 2. Now let's actually do a calculation to check this. So C is then equal to A times B, and it's equal to 1, 2, 3, 4 multiplied by 2, 0, 1, 2. Okay, so I expect to have 4 different elements here, 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 and here. So to obtain the C11, so it is C11 in here, what I need to do is that I need to look at the first row and the first column in here. So first row from A and the first column of B. And I'm doing the dot product, which means 1 times 2 plus 2 times 1. 1 times 2 is 2, 2 times 1 is 1. So here I'm getting 1 times 2 plus 2 times 1, which basically gives me 2 plus 2, and that's equal to 4. So here I'm just writing down 1 times 2 plus 2 times 1. Now, when I want to get this value, which is C12, this means that I want to get the first row and the second column. And that's exactly what I'm doing. So I'm going back and I'm saying, let's look at the first row, but this time we will look at the second column coming from the matrix B. So 1 times 0 times 0 plus 2 times 2. And then I do the same, only this time for the second row, which means I'm picking this row and then this column. So it is 3 times 2 plus 4 times 1. And for the final element C22, I'm taking the second row and then second column, which gives me 3 times 0 plus 4 times 2. Now, what does this give me? This gives me this 4 by 4 matrix, where 1 times 2 plus 2 times 1 is 4, 1 times 0 plus 2 times 2 is 4, 3 times 2 plus 4 is equal to 6 plus 4, which is 10, and then 3 times 0 plus 4 times 2 is equal to 8. So let's check. 4, 4, 10, 8. That's exactly what we have here. So as you could see here, the idea is that every time to follow what element I'm looking for the Cij, and then I just go to the each rows from the first matrix and the jth column from the second matrix, and I do the dot product of the A and then I and then K, let's say. So I'm going to the each row from the first matrix, and I'm taking all the elements, which means I don't even need to mention this index. It just means the entire each row coming from the matrix A. And then I'm doing the dot product between this row and the column that comes from the matrix B, which means B and then J, which then will give me the Cij. So I'm looking at this and taking this, multiplying this dot product, and this gives me the first element, then the first row, and then the second column, which gives me the second element in the first row in my matrix, so this one, and so on. So hope this makes sense. If it doesn't, make sure to reach out, because it's a very important concept. And let's also look into another example to make sure that we got this right. So in this case, as you can see, we have another matrices, so set of A and B matrices, again 2 by 2, a simple one, and we want to know what is AB. So let's say we call this C. We already know C should be 2 by 2, and what we are doing is basically for C11 we are saying let's look at the first row, so first row, and the first column coming from the second matrix B, and let's do the dot product. So 2 times 1, 2 times 1, 2 times 1, 4 times 5, 4 times 5, we get this. And then when we want to find what is C, what is C, and then 1, 2, so in the first row, but in the second element in our final matrix, so I is equal to 1 and J is equal to 2, it means we need to look at the first row from the matrix A, but this time the second column from the matrix B. So it is 2 by 3, 2 by 3, 4 times 7, 4 times 7. And this gives us a number 34. Even if you calculate, you can see that 2 times 1 is equal to 2, 4 times 5 is 5, so 4 times 5 is 20, so 2 plus 20 is 22 in here. And then you can do the rest of calculations, and this will be a good practice to see how we can do a basic matrix multiplication. The idea is actually quite straightforward when it comes to multiplying it. It comes with a practice when we see all these much bigger matrices. So this is another example. I will leave this one to you to complete it. Just to keep in mind, we always look at the dimension first. In here, 2 times 2 and 2 times 2, which gives me an impression already what I can expect. The result will be 2 by 2. And when it comes to the cross elements, just ensure to always look to the ith row and the jth column. This comes from matrix A and this comes from matrix B. Take them, compute the dot product, and then you will find your your final result. Let's call it Kij, because in this case we have a matrix C already. Welcome to the module 4 of this course when we are talking about matrices and linear systems. So in this module, we are going to dive deeper into this idea of linear systems with matrices and solving linear systems using different techniques. And specifically, we are going to learn the concept behind solving linear systems using matrices named Gaussian elimination and Gaussian reduction. Welcome to the module 4 of this course when we are talking about matrices and linear systems. So in this module, we are going to dive deeper into this idea of linear systems with matrices and solving linear systems using different techniques. And specifically, we are going to learn the concept behind solving linear systems using matrices named Gaussian elimination and Gaussian reduction. So we are going to solve linear systems with M equations and N unknowns using this idea of augmented coefficient matrix and then reduced row echelon forms. And we are going to see many examples. We are going to solve these problems and we are going to do it step by step, such that this very important concept from linear algebra will be entirely demystified for us. So we are going to learn each of these concepts one by one, and we are going to solve different problems like before with examples, such that at the end of this module, we will be clear on how we can use this idea of Gaussian elimination and Gaussian reduction in order to solve a linear system with matrices. So, solving linear systems is crucial in linear algebra for many reasons. It helps to provide this fundamental method for understanding and working with linear equations, which are the fundamental and the backbone of various mathematical, but also the applied sciences like statistics, data science, machine learning, deep learning, and in general, artificial intelligence. So here is a high-level overview of its importance and applications. So it's a basic but essential part of linear algebra. It introduces key concepts such as matrices, vectors, determinants. So we need to know and we need to incorporate all these different concepts that we already learned as part of previous modules in here, because we need to know the idea of matrices, the dimension of the matrices, this idea of coefficients versus unknown, so variables in our model, homogeneous versus non-homogeneous, how we do the indexing, so coefficient labeling in our matrices that we learned before. We also need to know this multiplication between a matrix and a vector, multiplication between matrix and matrix, the idea of transpose, and all these different topics that we saw before coming to this specific module. So the solving linear systems has a wide range of applications when it comes to the usage of it beyond linear algebra, because it's being used also as part of many other linear algebra concepts, including the dimensionality reduction techniques, the composition techniques like eigenvalues, eigenvectors, all these different mathematical and linear algebra concept itself, they rely on this idea of solving linear systems with matrices. But we also go beyond the application mathematics when it comes to solving linear systems. It's used in physics, it's used in engineering, and just in general, also even in finance, economics, in different investment strategies when we are talking about quantitative finance and using data as well as linear algebra in order to understand what kind of investment decisions we can make. So in order to set some constraints or objectives. And in the essence, solving linear systems is kind of this getaway to both understanding deeper mathematical theories, but also applying these concepts to solve real-world problems across various disciplines and domains, including data analytics, data science, machine learning, deep learning, artificial intelligence, and much more. So without further ado, let's get started. So we will start with the refreshment of the general linear system that we saw when we were beginning this unit. So we saw that we could represent a linear system with M equations and N unknowns with this format, where we said that we had this M equations, so you can see we got in total M rows, and we got N unknowns, which we were referring to the columns. So then we also saw this idea of indexing Aij, where I was the index corresponding to the row, and then J was the index corresponding to the column. And we said that these coefficients A11, A12 up to A1n, and then the same holds for all the other equations or the rows. These were ways for us to understand where exactly we are in our system, what is that the variable corresponding to which we are dealing that coefficient, and what that coefficient will basically tell us in which equation we are and corresponding to which variable or unknown we have the coefficient. Because this A11 holds entirely different information that is A23, and then this AMN. This AMN tells us in the mth equation what kind of information we know and the relationship between this when it comes to the nth variable or nth unknown. So this A11, A12, all these AIJs, those are known because we are saying we can estimate them. Those are constants. They come from R. Whereas the x1, x2 up to xn, those are variables. Those are things that we assume that either we don't know, or in the future we will see that those are basically the features that we got in our data. And then this B1 and B2 up to Bm, so far we have been kind of ignoring them. We already touched upon this when we were differentiating this idea of non-homogeneity and homogeneity of our system. But in this specific module, we are going to finally make these B's in use. We are going to make use of them, and we are going to see how we can transform this general linear system into concepts like matrices and vectors that we already have seen at the end of the previous module. So we are going to bring all these different topics together to solve this general linear system. And very soon it will also become much more clear why we want to do that. Because solving linear system, it means that we are getting an understanding what is the exact relationship between these coefficients and the unknowns. Now keep this notation in mind where we have all these different equations. You notice here the pluses. So we have the common notation of equations that we know from high school and pre-algebra, because we are going to transform these linear systems into matrices and vectors and the products of them. So we are going to go from this simpler notations to a bit more fancy notation, and we are going to bring our linear algebra into use in order to solve a system of m equations with n unknowns. So let's go to that bit more advanced notation. So here we go. So this is the matrix representation of linear systems. And a linear system of equations can be represented compactly using these matrices. So we already have seen this matrix. This is very familiar to us. We have been using this a lot. And this is the m by n matrix A. So this is the matrix A. You can note here we have A11, A12, up to A1n, and then we have all these different rows and the columns. So another thing that you can quickly notice is that we are dealing with a similar dimension for matrix A. So we have m by n. You can see we have m rows and we have n columns, something that you can note when you are looking at the last column and the last row. And then keeping in mind that we have always Aij, where the A is the row index and then J is the column index. So that gives us understanding what is the dimension of A, which is m by n. And then we have now a new component here. We see something new here, which is this vector. So we got a column vector here, x1, x2 up to xn. So we already see here from the last element that most likely we are dealing with an n by 1 vector. And how I can know this and how I can be assured by this is because, first of all, the index is n. And secondly, we already have learned for us to be able to multiply a matrix with another matrix or matrix with another vector, the middle elements of the two, so those things, they need to be the same. So we have learned that the number of columns of the first multiplier, in this case the matrix A, needs to be equal to the number of rows of our second multiplier, in this case the number of rows of a vector x. So you can see it in here. So here we got n columns as part of matrix A. Here we got n rows as part of vector x, which does make sense, which means that if we are writing like this and we are multiplying the two, then we are indeed dealing with a case when those two should be the same. So we are definitely safe to assume that our vector x, it needs to have n rows and only one column. So, of course, the one could have been different, but we have already seen another thing before. So why do we know that this is right and we are indeed dealing with a single column vector? Well, if we go back in here, we are simply taking this system and we are trying to rewrite it in this form. And what have we seen here? That we only got n different unknowns, something that was also given, which were x1, x2, up to xn, which we can also rewrite in this format, x1, x2, up to xn. So basically a column vector. That's exactly what we have done here. So we have taken all the x's and we have put it in the vector. And we are saying, let's multiply this matrix with this column vector and we will get this. And how we can know this? Well, let's first look into this first part and then we will understand why we have here this vector of b's. Let me clean this up. Well, what we have done simply here is that we have rewritten this part as a multiplication of a matrix and a vector. So we have said, let's take this. We have already learned how we can perform the multiplication between a vector and a matrix. We have seen that and how we can do that. Now we are basically doing the opposite. So we have already the final version. We have all these equations. You can see that we have taken a11, we have multiplied with x1, a12, we have multiplied with x2, and a1n, we have multiplied with xn. So basically what we have done here is that we have taken the a11, a12, and then a13, ... and then a1n. We said, let's take this and then multiply with x1, x2, ... xn, which is basically the dot product of this row vector with this column vector. So only the first equation can be rewritten as a dot product between this vector that we see in here and this vector. All right, perfect. But you can say, well, we not only got one equation, but we got m equation. This already gives us an idea what we have done in the left-hand side. What I just did for one equation, we can also, of course, do for multiple equations. So basically, what we have done was that we have said for equation 1, or I can also say for I is equal to 1, we have taken a11, a12, ... a1n, because we got n columns or n unknowns, and we multiplied this with x1, x2, ... xn, and this dot product, this is basically a1 vector and then t and then x, if we call this x. And then this, if you open this up and if you calculate this, you will see very quickly that you get a11 x1 plus a12 x2, ... a1n xn. This is simply the proof how we can go from here to here. Now, if we show the same, in the same way, you can actually go ahead and prove for yourself that I is equal to 1. We simply have this vector a11, a12, ... a1n multiplied by x1, x2, ... xn. But we also have the same for I is equal to 2, only with a different row vector, which is, of course, a21, a22, ... a2n, and then dot product with x1, x2, ... xn. So basically, the column vector x doesn't change, but we need to change the coefficient that comes. Because in each equation, we have different set of coefficients corresponding to this x unknowns. You can see that here coefficients are different. Their I, or the row index, is changing because here we have I is equal to 1, then I is equal to 2, ... I is equal to 1. I is equal to m. In the same way, here we are also doing the same. So here you can see we have exactly the same story, only now A is equal to m for our last row, which is A m1 and then A m2 ... and then A mn, and then multiply, so the dot product with x vector, x2 ... xn. Given that for all these cases we got the same column vector, you can easily see how we, instead of writing down these equations as separate row vectors, we have seen also the same doing previously, and instead we will just create one coefficient matrix. So we can say, instead of just doing this separately, we are also safe to do it in a combined way. So therefore, we are rewriting this all, and we are saying we can rewrite all these equations now as A11, A12, ... A1n. So as I had before, so I'm taking just this part, and I'm adding here my column vector that I had to multiply this A1t x2 ... xn. So basically I'm just taking this that we had and I'm writing over in here. So this is my first row. But then of course I can also add, there is nothing that I'm changing if I'm adding similar story, only this time I'm using this second row vector, A21, A22 up to A2n, because at the end of the day I'm doing similar multiplication with x in here too. So A21 and then A22 ... A2n. And then of course the same holds for AM1, AM2 for my last row, and then up to AMN. So if you open this up, you will quickly see that what you will get is that for the first equation, I will get entirely separate amount. So A11, x1 plus A12, x2 ... plus A1n xn. So I'm simply computing the dot product between this row vector and this column vector. We have already seen how we can do a calculation like this. This should seem very familiar. Now I'm only doing it at a scale. So I'm adding here also the second row. So A21, A22 ... and then A2n. And then here, of course, I forgot to add the x's. So A21 times x1 plus A22 times x2 plus ... and then A2n and then xn. And then I'm doing this all the way down to the last row, AM1, x1 plus AM2, x2 plus ... and then AMN, xn. And then what I'm doing is that I'm saying this is equal to this. You are free to check it yourself. You can see that once you write down even all the smaller elements in here, you will see that you are getting exactly the same. This is simply another way of writing that you will take all these different vectors, A1t, A2t, so transpose ... and then you also represent your last row by a vector. And then you take this, which is basically m by n, and then you do dot product with a vector x1 and x2 ... xn. And why am I allowed to do so? Because I have m different equations. So equation 1, equation 2, ... equation 3. Those are the coefficients of those corresponding equations. And those are the unknowns. And given that the unknowns are exactly the same across all the equations, so as you can see in here, the unknowns, they don't change. So this means that every time I need to compute the dot product between a different coefficient, so A11, A12, and then it changes to A21, A23, A2n, but the unknowns, they do not change. So the vector, the unknown vector that I need to multiply them, it doesn't change. Every time it's this. So in here I have the same, in here I have the same, and in here I have the same column vector. This means that I can simply rewrite this set of dot products into a larger system where I have this coefficient matrix, which is A. So and we are calling it coefficient matrix, we saw already before. Why? Because those are the coefficients corresponding to the unknowns. We are just storing them in one place. And then we are storing the unknowns, x1 to xn, in the column vector because we got n unknowns. And then the final piece of this puzzle is what we see in here in the right-hand side after the equation sign. Of course, I'm talking about the b's. So we got here b1, b2 up to bn. You might have already guessed that we are dealing with a vector, not a matrix, because we got m equations and m b's, which means that we can represent this as b1, b2, bm as a column vector with m rows, because we got here 1 row, 2 row, here m row, and then by, given that it's just a one column, here 1. So basically we are saying for equation 1, a1, 1, a2, 1, 2, a1n multiplied, so dot product with x, so x1, x2 up onto xn, this should be equal to b1. This is exactly what we have. Let me clean this up. This is exactly what we have here. We say a11 x1 plus a12 x2 a1n xn is equal to b1. That's what we have here, because we are saying the dot product of this row vector that we have just used to rewrite this thing. Dot product of this coefficients with the corresponding unknowns is equal to b1. And we have already seen that it is simply this thing that we are rewriting. This first equation we have is equal to b1, as you can see in here. Therefore, when we do exactly the same, it's simply equal to here b2 for the second equation, and then here is equal to bm. So given that from the left-hand side here, we already have seen that this is simply equal to coefficient matrix A, and then dot product with x, where x is this vector. It means that we can also take over this equal sign from here, and the only thing that is left from us is to represent this column vector in here, which we can call a vector B. And that's exactly what is in here. So we soon will also see the clear definition of it, but for now, let's see how we have used this linear system in order to transform it in the notation with matrices. So we have taken these coefficients, and we have seen that in here, we can represent these coefficients as a vector, a row vector, so a11, a12, a1n, multiplied with a column vector x1, x2 up to xn. So this is exactly the first equation, the left-hand side. So we say that this is the first dot product, this is the second dot product, up to the last row, the last dot product. So we have already represented this dot products as multiplication, so product of a coefficient matrix A by column vector containing all these unknowns, x1, x2 up to xn, x. And we said, let's take over this equal sign. And given that the same logic row-wise holds also in here, so we say, this is row 1, this is row 2, row m And everything that holds here for the rows holds here as well. We need to take over everything in a consistent way. Therefore, we are saying let's also represent this in terms of the vector, if we are doing that in here. Therefore, we are calling this a B, and these B's are just real numbers, B1, B2 up to Bm. And this is how we can transform and we can rewrite this system with m equations and n unknowns into a product in terms of matrices, so coefficient matrix A, a column vector containing the n unknowns, and then a vector, a column vector B that contains all these different values, B1, B2 up to Bm. So this is basically rewriting what we have in here. Hope this makes sense, but if it doesn't, we are going to see this again in the definition. I just wanted to warm up with this before we move on to the official definition. So, a linear system of equations can be represented compactly using matrices, and we just saw that. An m by n matrix A multiplied by an n vector x results in an m vector B. So you can see it in here. So this is an m by n matrix A. This is the n by 1 column vector x. And this is the m by 1 column vector B. And one thing that we can see very quickly is that what we are doing here is that we are transforming that equations into a matrix representation, but nothing changes with the equations. We can still write them down like that. It's just by using matrices and vectors, we will soon see how we can use this in order to solve this problem. So, why are we doing this? When we have just two equations with two unknowns, we know from high school that we can quickly solve that. We can just write down, for instance, x1 plus 2x2 is equal to 3, and then 3x1 plus 4x2 is 6. We can quickly solve this problem by, writing down the x1 in terms of 3 and 2x2, filling that in here in the x1, and then solving the problem because we got two equations with two unknowns. The problem become much more complicated when we got 3 equations with 3 unknowns, 5 equations with 5 unknowns, 100 equations with 100 unknowns. Therefore, to do this solving of the system of equations at the scale, we need this matrix notation. And that's exactly what we are doing in here. So let's also quickly check the dimensions such that we confirm that we are on the right path before moving on to the practical material. So here we got matrix A containing the coefficients from our linear system, and it is, let me remove this, it is m by n. Then we got our x. So this thing is a column vector containing the unknowns in our system, and it contains n rows. So the x has a dimension of n by 1. It's a single column vector. And we are saying this is equal to, and that's just given, that's how we transform our linear system into this notation. This is equal to a column vector B, and the dimension of it is m by 1. Now let's check whether this makes sense. We know that already, and we just said that this 2 needs to be equal. It's fine. So we have the this criteria satisfied. So the number of columns of matrix A, coefficient matrix A, is equal to n, and then the number of rows of column vector x with unknowns is equal to n. So we can indeed do the multiplication. So we are correct in that notation. But is it true to claim that indeed here we got m different rows? Well, we have learned that if we take m by n matrix and multiply it by n by 1 vector or matrix, then what we are getting is that we first take over this, so the number of rows, this will become the new number of rows of our final matrix. And then m by, and then this last element, so the number of columns of our last item, so in this case, dx, so it's equal to 1. This is our final number of columns. So the new dimension then becomes m by 1. And what do we see here? That indeed the result that we say, we claim that this amount is equal to is m by 1. Because if we are saying that the two amounts are equal to each other, then naturally they should have the same dimension. So a times x will have a dimension m by 1, which is coherent to what we are claiming that is equal to, which is m by 1 column vector b. Alright, so now when we have refreshed our memory on that dimensions, we are ready to move on to the next slide. So now we need to solve this linear system. So we need to find this set of unknowns that will help us to identify and clarify all the unknowns in our system. So one way, and the infamous way of solving this linear system, is what we are referring as Gaussian elimination. Gaussian elimination is the systematic method for solving linear systems. It basically transforms this system into what we are referring as row echelon form, from which the solutions can be more easily identified. So in the next couple of slides and lessons, we are going to learn this idea of elimination. We will understand why is it actually called elimination, which is quite intuitive once we see the examples. And also we are going to learn this idea of row echelon form, reduced row echelon form, because those are very important concepts to understand this entire idea of solving linear systems using linear algebra. So before moving on to that, we need to know the basics, one of which is the idea of augmented coefficient matrix. So by definition, the augmented coefficient matrix of linear systems AXB combines the coefficient matrix A and the vector B into one matrix. So you can see here the matrix A, and then we have here this straight line, and then B. This is basically this entire augmented coefficient matrix. It's a fancy way of saying, let's take all the unknowns from our system, which are the coefficients in our system, and then the constant in the B's. So I have to say not nouns, but rather the values, so the scalars, coefficients. And let's take the coefficients in our system, which are represented in our coefficient matrix. And let's combine this with the information that we got in our system, which is the B1, B2 up to Bm. And let's combine the two, and we call it augmented coefficient matrix. So we are simply taking the coefficient matrix A. You can see A11, A12 up to A1n, and then also in the last row AM1, AM2, AMn. This should look very familiar because it's just simply this matrix, matrix A. We are taking it over in here. And then we are saying, let's draw a straight line. And then add here the column vector, our result vector, which is B. So we saw in here that is this thing. So let's take this part and this part, put a straight line in between, and this will become our new matrix. So as you might have already guessed, in the matrix A, in the coefficient, we got m rows and n columns, which means that our new matrix will have at least m rows and at least n columns. Now, given that we are adding yet another column at the end, it means that the number of columns will increase, but one thing that is important to note is that the number of rows will not increase because both the coefficient matrix and the column vector B, they have the same amount of rows. They both got just m rows. So let me actually rewrite this. So we know that A is m by n. So it has m rows and n columns. And we know that B is m by 1. which means that it got m rows and one column. This means that if we combine horizontally, so if we put them together next to each other, the coefficient matrix A and B, this means that we will end up with the same rows. So we still have m rows, but now we will have n plus 1. So here are the n columns from our coefficient matrix A, and here yet another extra 1 column that comes from the vector B. Therefore, we get the augmented coefficient matrix that has a dimension m by n plus 1. So this matrix is key when we are applying these different row operations to solve our system of m equations and n unknowns. So we are basically bringing all these values in order to solve our problem and find the unknowns. Now, before moving on to actual definition of row echelon form RREF, I wanted to provide here an example. So how we go from this system of equations into this new form A times X is equal to B, and then how we can represent our matrix into this idea of augmented coefficient matrix. So let's assume we have the following system of equations. So we got x1 plus 2x2 plus x3 plus x4 is equal to 7. And then we got x1 plus 2x2 plus 2x3 minus x4 is equal to 12. And then 2x1 plus 4x2 and then plus 6x4 is equal to 4. Let's now first write these equations with 3 equations and then 4 unknowns into this system where we transform this into these matrices and the vectors. So let's write it in this format of Ax is equal to B that we saw before. And then we will also write this in the augmented coefficient matrix. So given that I know that we have 3 equations and 4 unknowns, the first thing that I will do is that I will get my coefficient matrix A. So for A, what I need to do is that first I need to understand what is the dimension of it. And how can I know the dimension? I know that it should be m by n from the theory, where m is the number of equations, the number of rows, and n is the number of unknowns. I got 3 equations, 4 unknowns. So this is 1, 2, 3, and 4, x1, x2, x3, x4. Those are my unknowns. This means that I already know exactly what the dimension of my coefficient matrix A should be, which should be 3 by 4. Let's now go in and search those values and fill in here to get our coefficient matrix. So here I see that x1 has a coefficient of 1. So whenever you don't see here a value, it means we have 1 times that variable, because 1 times a number is simply that number. So here I got 1. And then for 2x2, I got 2. For x3, I got 1. And then for x4, I also got 1. And do keep in mind that in the columns, I have to have the coefficients corresponding to these unknowns, x1, x2, x3, x4. This will be kind of a guide mentally to check every time whether we are dealing with the right coefficients. So then we go on to our second equation or our second row, which means I got 1 in here. See here, 1, and then 2, 2, and then minus 1. And then here for my third row or third equation, I got 2 for x1, I got 4 for my x2, I got nothing for my x3, which means that it is 0, because 0 times a variable is equal to 0. And then finally, for my x4, I got 6. So now I have my coefficient matrix. We can rewrite very quickly the column vector containing the unknowns. We already know what the dimension of it should be because we have 4 unknowns. So it should be 4 by 1. And it is x1, x2, x3, and x4. And this is my x. And finally, I see what my b is here. So we got 3 equations. So we remember that the dimension should be m by 1, which is corresponding to what we also see here. It's coherent. We got 3 b's for 3 equations. So therefore, I'm saying my b is equal to, it is 3 by 1 column vector, and is equal to 7, 12, and 4. Now, the final result is simply, let me rewrite this in the form that we just saw. So I can write these equations, this system of 3 equations with 4 unknowns as 1, 2, 1, 1, 1, 2, 2, minus 1, 2, 4, 0, 6, multiplied by x1, x2, x3, and x4, equal to 7, 12, and 4. This is in the AX is equal to B matrix notation. So this is the first part. Now we know how we can rewrite the system of linear equations with m equations and n unknowns into this form of AX is equal to B. Let's now try the next step, which is writing this system, rewriting it into this augmented coefficient matrix. So I want to get this A, B. This one is actually quite straightforward now when we have our A and the B, because what this augmented coefficient matrix represents, it's simply taking the matrix A and then adding the vector B next to it in order to get our final A plus B matrix. So not A plus B, but basically A and then next to it the B. So what is my A? It is this thing. So it is 1, 1, 2, and then 2, 2, 4. I'm just taking over this. 1, 2, 0, 1, minus 1, and then 6. So now this is the A with 3 rows and then 4 columns. And then here, I'm simply putting this straight line, like in here, and then putting the B in there. And the B was this. So 7, 12, and 4. So 7, 12, and 4. This is the B, which was 3 by 1. 3 by 1. So 1 column and then 3 rows. Which means that this final matrix, the augmented matrix AB, it should have 3 rows and 5 columns. So it's really important to distinguish the multiplication and this unique form, which is called the augmented coefficient matrix. So here we are not multiplying or adding, we are simply taking the coefficient matrix that we just found, A, next to the vector B. And given that they both have the same rows, that's very straightforward and easy. So this is about the augmented coefficient matrix. Let's now move on to the next concept, which is the row echelon form, or RREF in short. So matrix A is in a row echelon form if all non-zero rows are above any rows of all zeros. So all non-zero rows are above any rows of all zeros. Each leading entry of a row is to the right of the leading entry of the row above it. and all entries in a column below a leading entry are zeros. The leading entry in each row is known as the pivot or corner entry. Now, this is a whole mouthful, and the concept itself is not straightforward when it comes to this definition. But once we do the actual examples, all these concepts will be clear. And when we solve these multiple problems, and we are going to solve like 3 till 5 problems, it will become easier to understand this concept of row echelon form, what we mean by pivot or corner entry or pivot vector, what we mean by having all these entries in a column below a leading entry zeros, or what we mean with this concept of all non-zero rows being above any rows of all zeros. So in terms of the words, this might seem a bit complicated, and it is, but when we look into the example, this concept will be demystified. So once we have the RREF, which will be, we will come back in a bit, and we will look into the example to clarify this definition. Let's quickly look at the next step that we need to perform, which is the reduced row echelon form. So here you can see that this reduced is what is basically added in front of the row echelon form. So this was the row echelon form that we will now be discussing. And then once the row echelon form is done, we basically do a reduced row echelon form. So that is the next step. And by definition, a matrix is in reduced row echelon form if, in addition to the row echelon form, so RREF, we also have every leading entry in a row that is equal to 1. Also, we are calling that we have a leading 1. And each leading 1 is the only non-zero entry in its column. So RREF, or the reduced row echelon form, it simplifies the system for easier solution derivation. So in terms of explaining or in terms of formulating, the RREF doesn't really sound that convincing because we need to demystify all these different concepts. So my suggestion would be, let's move to the actual practical problem. And once we solve this step by step with all these details, all these different criteria, this 1, 2, and 3, and then the 4 and the 5th criteria, they will be demystified and will be very clear to you. Let's now solve another problem, a similar one to what we just solved, only this time we will go a bit faster through all these steps just to ensure that our understanding of solving a linear system with this multiple equations and multiple unknowns using this idea of Gaussian elimination, reduction, and all these different steps up to the point of the reduced row echelon form, we can go through quickly, and we will ensure that we end up with the solution to the system using those techniques that we have just learned. So here is my system of 3 equations and 3 unknowns this time. And like we learned before, the first step is to transform this into this augmented matrix. But first, of course, I need to know what is my A and what is my B, because transforming this and writing this in the augmented matrix form, A and then B, it means I need to know what is my A and what is my B. So let's write the first step down. So my step 1 in this case is to write it in the augmented, so augmented matrix. And for that, I need to know what is my A. So my A is equal to 1, 1, 1, and then 2, 3, 1, and then 1, minus 1, and 2. This is my A, which I take from all these coefficients that I see in here. And then my B, I can see in here from all these values. So it is 6, 14, and 8. This means that my augmented matrix is A and then B, and it's equal to 1, 1, 1, and then 2, 3, 1, and then 1, minus 1, and then 2, then a straight line, and then 6, 14, and 8. This is my augmented matrix. This is my first step. So let me go ahead and remove these details, because then I can take this over and I can then simply continue. So my augmented matrix is then 1, 1, 1, and then 2, 3, and then 1, 1, minus 1, and then 2. And then I have the values for my B, which is 6, 14, and 8. Alright, so first step is done. Now we are ready to go on to the next step. Step 2, which is to apply all sorts of operations, and ideally by every time normalizing each row, so every time ensuring that here the leading entries are ones. We call it normalization. And then by elimination. So we saw that every time we were eliminating some of the variables to ensure that we will end up with the zeros in the lower diagonal of our augmented matrix, and we will have only the leading ones in our only a single one and a leading pivot value, so the pivot entry in our augmented matrix per column. It will be the only element that will be non-zero, and the rest should be all zero. So here I'm talking about performing all these different operations to ensure that we create and we come to this point of the row echelon form, and then from there we will go to the reduced row echelon form, so the RREF that we saw before. So let's do that. So the step 2 will be to get the REF of A. Or rather, I have to say RREF. Maybe we can combine the two and do it at the same time. So for that, what I will do is that, like before, I will just draw this line, because this will help me to keep track of all the operations that I'm performing later on to check. One thing that we can notice here, that the first row is already normalized, which means that I have a 1 in here. So I'm happy with that. I won't do anything to it. So what I need to do is to move on the elimination of this x1 from the row 2 and row 3. So I need to find a way to ensure that this entries become 0, because I want to get here 1, 0, 0. So I want to have a single pivot entry in here, and the remaining values in this column under this one should become 0. So how can I do that? The first thing that I can do to eliminate this x1 from row 2 is subtract from this 2 times the row 1. So you can see that if I take this row 2, so this is my row 2, this is my row 1, and this is my row 2, this is my row 1, and this is my row 3. If I take row 2, this is my step 1. Row 2 is equal to, and then I take the row 2 and I subtract from this 2 times row 1. Let me remove this to open up some space. So if I take this row and subtract 2 times this one, then what I will get is two minus 2 times 1, which is 0. 3 minus 2 times 1, so 3 minus 2 is 1. And then 1 minus 2 times 1, which is minus 1. And then when it comes to the value of B, 14 minus 2 times 6, so 14 minus 12 is 2. So this is what I'm getting. And then given that I have already a normalized first row, so I have already 1 in here, I will just take this over for now. And then for the last column, for the R3, in order to normalize that one, and in order to get rid of this 1 from here, so first thing I want to do is to eliminate the x1 from here, which means I need to get rid of this 1. And how can I do that? I can simply take the row 3, so R3, And I can subtract from the R3 the R1 because both have 1 in here and this one. I can simply take this and then remove and then subtract from this the first row. I can then end up with basically a 0. So here, if I take this one, I got this one, and then I subtract from this 1 times 1. So 1 minus 1 is 0. Minus 1 minus 1 is minus 2. 2 minus 1 is 1. And then 8 minus 6 is 2. This is what I get after performing these eliminations. Hence also the name Gaussian elimination. So using these eliminations, we are then getting rid of certain elements and certain variables. So this is what we get after performing these row operations. And now we are ready to go on to the next stage. So we see now that in this specific case, the row 2 is already normalized, which means that here we already have a 1, so we are happy with that. We want it to be like that. So I already see another coefficient that I want to get rid of, that I want to eliminate from, x2, which is this one. So I want to get rid of this minus 2, and I want it to become a 0. And one way that I can do that is to take this row 3 and then add 2 times row 2 to this row 3. So why am I not taking row 1? Because row 1 has a 1 in here. And if I take that, I will then basically bring me back to the point where I'm having here an element, because 0 and then adding something that is related to this first row or subtracting from it a multiple of this first row, it will always lead me here, this 0 becoming a non-zero value. That's something that I want to avoid. Therefore, I want to perform some sort of operation to this row 3 by using row 2, because that's my only way to eliminate this minus 2 from here without hurting my 0 here. And therefore, I'm looking at this row that already contains the 0 here. So that's great. And I'm going to use row 2 to eliminate this minus 2. And the way that I can do it, given that here I have a minus, so I have minus 2, I need to add to this 2 times row 2. So in the step number 2, I will then say that my R3 is equal to R3 and then plus 2 times R2. So let's go ahead and see what that gives us. So 0 plus 2 times 0 is 0. And then minus 2 plus 2 times 1 is minus 2 plus 2, which is 0. So I'm already getting rid of the minus 2, which is great. That's exactly what I wanted. And then 1. Here I have a 1. So 1 plus 2 times minus 1. So 1 plus 2 times minus 1. That gives me 2 minus 2, or 1 minus 2, which is minus 1. So I'm getting here a minus 1. And then here, when it comes down to the B element, so I'm talking about this specific element. So 2 and then plus 2 times 2, so 2 plus 4 is equal to 6. So here I'm getting a 6. Okay, perfect. So let me take over the row number 2. It's already normalized, so I already have a 1 in here. So 0, 1, and then minus 1. And here I got a 2, so I just simply take over. I'm not doing anything at this stage to that row number 2. So, now the question is whether there is something that I need to do to my row 1. Well, the question is yes, because in our definition we saw that we wanted to have this element ideally being 0, because we need to have here a 0 for this column to have a single element of 1 in the pivot entry, which is this one, which means that I need to make somehow this element 1 that we see in the row 1 being equal to 0 at this stage. Let's see how we can achieve that. So we got a 1 in here, and we got a 1 in here. So one thing that we can do is to take row 1 and subtract from that row 2. In that case, I won't do anything to my first entry, my pivot entry for my first row. I won't do anything to it because 1 minus 0 is 1. But then I will get rid of this 1 because 1 minus 1 is equal to 0. So let's go ahead and do that. So R1 is equal to R1 minus R2. So in that way, if I do 1 minus 0, I'm ending up with 1. 1 minus 1 is equal to 0. So I'm getting what I just wanted. And then 1 minus minus 1, it is 2, because it becomes plus 1 plus 1. And then 6 minus 2 becomes 4. So this one becomes 4. This is the end result after performing these operations in step number 2. Perfect. So now let's see what else we got in here that we want to change. Let me make this line longer. All right. So there is something that I still want to do in order to normalize the last row. Because here, instead of having 1, I have minus 1. So firstly, I need to multiply this row by 1, simply by a scalar, in order to ensure that I can have 1 in here instead of just minus 1. So in step number 3, I will do R3 is equal to minus 1 times R3. So I will get 0, 0, 1 given, and then 6 times minus 1 is minus 6. Now, what else we need to do in terms of the rest of the values in our augmented matrix? So we got 1. Let me actually write it over such that we see what is going on. So I'm taking over this, and then minus 1, and then here I got 2. Then here we got 1, 0, 2, and then 4. All right, so this is our augmented matrix. And there are a few elements that we want to get rid of. It is this element and this one, because we want them to be equal to 0. And how we can do that? So we got 2 things to eliminate. We want to eliminate from the row 1 this 2, and we want to eliminate from this row 2 this minus 1. How can we do that? Well, for this row 1, we can already see that we got here this 1 from row 3. So it's super helpful in that aspect. So we can use that in order to get rid of that R2. So let me actually write it down. In the step 4, so step number 4, what we can do is to take R1, and it will be equal to R1 minus 2 times R3. Because here I got 1, and I can use this 1 in order to get rid of this 2. So 2 minus 2 times 1 is equal to 2 minus 2 times 1 is equal to 0. So I can get a 0 in here. And that's exactly what we want to do. We want to eliminate this x3. So we want to eliminate this from here, this 2 from this first row. That's something that we can achieve by this. And another thing that I can also see, let me free up some space in here. to write down these equations. So remove this. Given that the steps are already written, you can always replicate that. So then the new augmented matrix A will become, so here 0, 0, and then 1, I'm leaving the last row. It is already in a format that is desired. So I will leave that there. And then I'm going to update my first row. So first row, R1 is equal to R1 minus 2 times R3, which means it's equal to 1 minus 2 times 0 is 1. 0 minus 2 times 0 is 0. 2 minus 2 times 1 is equal to 0. And then 4 minus 2 times minus 6. So 4 minus 2 times minus 6 is equal to 4 and then plus 12, which is 16. So I'm getting a 16 here. And then for the second row, I also need to do elimination to get rid, this time, we remove this. This time I want to get rid of this minus 1, because then I will have criteria satisfied that this should also be 0, because this should be 0 for this pivot to be the only non-zero element in this column tree. Only then I can say that I'm dealing with RREF, so that I have my matrix in the reduced row echelon form. So for that, what I'm going to do is I'm going to make use of my third row again. So I'm going to take row 2, and I'm going to subtract from row 2. I'm actually going to add row 3 to it, because here I have minus 1, and if I have minus 1 to 1, I will just get a 0. So for that, I'm going to write that for the elimination, so for eliminating x3 from the second row, I'm going to write that the R2 is equal to R2 plus R3. So then I'm going to get here 0 plus 0 is 0, 1 plus 0 is 1, and then minus 1 plus 1 is 0. Now, why I have used actually the third row and not the first one? Because I want to ensure that I won't do anything to my 0 in here. If I do something with this first row, then I cannot do that. I cannot reach that. It's just counterintuitive, because I want to keep my work intact. I have worked in such a way that I can eliminate this x1 from the second row. And that's something that I don't want to go back to. Instead, I want to use something that is in the column tree to get rid of this value. And that's something that we could do by using this element. So we always look at the shortest and easiest path to get rid of a coefficient in our matrix, in our augmented matrix. Now, let's see what is left. So R2 is equal to R2 plus R3, which means that we need to add this 2 to this minus 6. And 2 plus minus 6 is equal to minus 4. Minus 4. There we go. So after performing all these steps, we end up with the following augmented matrix. And if you can notice here, we not just achieved the row echelon form, but we have actually achieved the reduced row echelon form of our A. This is that form, because we have on the entry, so our pivots are the ones in here, and we can see that all the criteria are satisfied. So here on the lower diagonal, so the lower part of our matrix are all zeros. And on the top of that, also all the elements in these columns, they are all 0 except of the pivot values, and they are all equal to 1. And that's exactly what we wanted to have in order to say that we are dealing with the reduced row echelon form. Perfect. So now we are ready to move on to the last final step to get the solution. And unlike the previous system, which was a bit more complicated and it had multiple infinite solutions, So you might recall this example where we had to describe the final solution using this x2 and x3, because depending on different values of x2 and x3, which could take infinite values, we then could get a different solution for our x vector. So we saw that when, for instance, the x1 is equal to 1 and x4 is equal to 3, then our solution was this. But then, of course, if the x2 and x4 were different, we would have gotten another solution, and the result of the linear system had infinite number of solutions. Unlike that one, this example is much more convenient, because even from the RREF of this, so reduced row echelon form of the matrix A, we can already see what is the solution of this problem, of this linear system where we had 3 equations and 3 unknowns. So we actually got to single solution. That's something that I can already see from here. And let's break it down to see how I see that solution. So we transform this to a system of equations. So we are basically doing it backwards. And now, after getting this RREF of matrix A, we are going back and we are going to rewrite the system with the unknowns x1, x2, and x3. So here I see 1, which means that the coefficient of x1 is 1. So 1, x1, which I will just write x1, x1, so I get x1 plus 0 times x2 plus 0 times x3 is equal to 16. And then 0 times x1 plus 1 times x2 plus 0 times x3. I'm writing down this 0 such that it will make sense what we are doing, and in case next time you have a different system, it will be easier to follow. So 0 times x1 plus 0 times x2 plus 1 times x3 is equal to minus 6. Now what is this? We get rid of all these zeros. So you can already see what is going on. We are ending up with x1 is equal to 16, x2 is equal to minus 4, and x3 is equal to minus 6. There we go. So we got our solution for x, which is x1, x2, x3 is equal to 16 minus 4 minus 6. This is the unique solution to our problem. And if we clean this up and we write down in a nicer term, so I'm going to remove this, then we can say that the solution for our problem, so this problem that we saw in here, so the x, which is equal to x1, x2, x3, it's equal to 16 minus 4 minus 6, which you can see it also here. So one trick is always to look into in here. If you have the identity matrix as part of your augmented matrix, then you have a unique solution to your problem. So you got 3 rows and you got 3 columns and you have all this identity, so these unit vectors, then this is the indication that you got a unique solution to your problem, and that solution is simply this column, as you can see in here. So next time when you have something like this, you don't even need to rewrite the transformation back to the equations. You can directly say that the solution to your system with these 3 equations and 3 unknowns is this one. So this column vector equal with this entry 16 minus 4 and minus 6. And that's the end of this problem. So in this way, we have learned how we can quickly solve this type of problems by just following this common procedure. And this ended up with a unique solution. So you can have cases when you will not have any solution, and that will be the case when we saw before too. So in case there is an equation that says that in the left-hand side, you have zeros, but then in the right-hand side, you have a number. So you end up with 0 is equal to a number, let's say 8. This cannot happen, which means that you are saying your system doesn't have any solutions. So let me actually write it down. So you can have 3 possible cases. Case 1, when you end up with one of your equations, and here you got numbers, let's say 3, 4, 5. And here this is 0. So basically you end up saying 0 is equal to 5, which is not something that is possible. So you say the solution is this. So it doesn't exist. It is also possible that you have case 2, when, like in the previous case that we saw before, in this example, you don't have all the unknowns expressed in terms of the other ones, which means that you don't have a unique solution to your system. So you can even see that from here. Therefore, you have here x2 and x4. So you describe your final solution as a linear combination of some of the variables that can take infinite amount of values. So x2 can be anything and x4 can be anything, which means that your solutions will also be infinite. So this case 2 will have infinite amount of solutions. And the case 3 is the case that we saw before. Right now, when we end up with this identity matrix in here and this corresponding amounts in here. So this gives us indication that we got the single solution. So single solution, a solution to your general linear systems.